There is a star 6 light-years from Earth that has been taunting humanity for more than a century. It is not bright. You cannot see it with the naked eye. It is a dim, ancient red dwarf, smaller than our Sun, cooler than our Sun, and so faint that it was not even discovered until 1916, when an astronomer named Edward Emerson Barnard noticed it creeping across photographic plates faster than any other star in the sky. It moves, not in the way all stars move, drifting imperceptibly over millennia, but with a visible, measurable urgency, crossing the width of a full moon in just 174 years. Astronomers call this proper motion, and Barnard's star has the largest proper motion of any known star. It is racing through the galaxy at roughly 110 kilometers per second, relative to our Sun, and it is heading toward us. In roughly 10,000 years, it will become the closest star to our solar system, overtaking even the Alpha Centauri system. 6 light-years, that is the distance. It sounds almost manageable. After all, Proxima Centauri, the current nearest star, sits 4.24 light-years away. Barnard's star is only about 40% farther. In cosmic terms, it is practically next door. It is the kind of distance that makes ambitious people lean forward and say, perhaps we could reach it. But we cannot. And the reason is not what most people think. The common explanation is that interstellar distances are simply too vast for our current technology. This is true, but it is also incomplete. It is the easy answer, the answer that allows us to imagine that someday, with better engines or faster ships, we will solve the problem. The real reason is deeper, more structural, and far more humbling. It involves not just the distance, but the energy required to cross it. It involves the fundamental limits imposed by physics on how fast anything with mass can travel. It involves the biological fragility of the human body, the engineering impossibility of sustaining a spacecraft for thousands of years, and the thermodynamic reality that every engine ever conceived is fighting a war against entropy that it will eventually lose. The distance is not the barrier. The barrier is the universe itself, the way it is built, the rules it enforces, the costs it extracts for every kilometer of progress through the void. 6 light-years. That is roughly 57 trillion kilometers. To write that number out in full, it is 57, followed by 12 zeros. If you drove a car at highway speed, 100 kilometers per hour, without stopping, without sleeping, without refueling, it would take you approximately 65 million years to arrive. 65 million years. That is roughly the same amount of time that has passed since the asteroid impact that wiped out the dinosaurs. You would need to drive for an entire geological era just to reach our nearest stellar neighborhood. Our fastest spacecraft, the Parker Solar Probe, has reached speeds of approximately 635,000 kilometers per hour during its close passes around the Sun. At that speed, the fastest any human-made object has ever traveled. The journey to Barnard's star would take roughly 9,200 years. That is longer than the entirety of recorded human civilization. The first cities were built roughly 6,000 years ago. Writing was invented roughly 5,000 years ago. 9,000 years ago, there were no nations, no empires, no written languages. Humanity was scattered across the globe in small bands of hunter-gatherers. The idea of maintaining a spacecraft, a crew, a mission, for a duration longer than the history of civilization itself is not merely impractical. It is a different category of impossibility. And the Parker Solar Probe is cheating. It achieves its extraordinary speed only during brief gravitational slingshot maneuvers around the Sun. Its average velocity on an outbound trajectory would be far lower. Voyager 1, the most distant human-made object, is traveling at roughly 17 kilometers per second, or about 61,000 kilometers per hour. At Voyager's speed, the trip to Barnard's star would take approximately 106,000 years. 106,000 years. Homo sapiens as a species is roughly 300,000 years old. The journey would consume a third of our entire species' existence. By the end of tonight, you're going to understand why Barnard's star, a dim red dwarf barely 6 light-years away, represents a barrier that no technology we possess or can reasonably foresee will ever overcome. You are going to understand the specific physics that makes this journey not just difficult but fundamentally hostile to everything we know about engineering, biology, and energy. And you are going to confront a possibility that most popular science carefully avoids stating plainly, that the stars may be forever out of reach, not just for us, but for any biological civilization anywhere in the universe. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Barnard's star sits in the constellation Ophiuchus, the serpent bearer. It has been studied for over a century. It has been the target of some of the most ambitious thought experiments in the history of space exploration. It was the destination chosen for Project Daedalus, the British Interplanetary Society's famous unmanned interstellar probe concept from the 1970s. It was selected precisely because it seemed reachable, because it was close, because it felt like the kind of challenge that human ingenuity might someday meet. But a century of study has only deepened the problem. The more we learn about interstellar travel, the more we understand just how implacably hostile the void between stars truly is. The distance is not empty. It is full of radiation, full of dust, full of silence, and full of time. And time, it turns out, is the cruelest obstacle of all. Now, let's begin. To understand why reaching Barnard's star is such an extraordinary challenge, we need to begin not with the star itself, but with the space between here and there. Because it is the space, not the destination, that defeats us. 6 light-years of interstellar void is not just empty distance. It is a gauntlet of physics, a testing ground that exposes every weakness in our technology, our biology, and our understanding of energy. Let us start with the star. Barnard's star was discovered in 1916 by Edward Emerson Barnard, an astronomer at Yerkes Observatory in Wisconsin. Barnard was examining photographic plates taken over a period of years, comparing the positions of stars from one plate to the next, looking for any that had shifted. Most stars appear motionless over human timescales, their movements too small to detect without precise instruments. But one star had moved noticeably. It was sliding across the sky at a rate of 10.3 arcseconds per year, faster than any other star known. This extraordinary proper motion is what made it remarkable, and it is what earned it Barnard's name. Barnard's star is a red dwarf, the most common type of star in the galaxy. Red dwarfs make up roughly 70 to 75% of all stars in the Milky Way. They are the workhorses of the cosmos, small, dim, and extraordinarily long-lived. Our Sun is an outlier, a relatively large and luminous star that will burn through its hydrogen fuel in roughly 10 billion years. Red dwarfs, by contrast, burn their fuel so slowly that they can persist for trillions of years. The universe is only 13.8 billion years old, which means that no red dwarf that has ever formed has yet died of old age. Every red dwarf that has ever ignited is still burning. They are the most patient objects in the cosmos. Barnard's star specifically has a mass of roughly 0.16 solar masses, meaning it weighs about 16% as much as our Sun. Its radius is roughly 0.19 solar radii, making it about 19% the width of the Sun. If the Sun were the size of a beach ball, Barnard's star would be roughly the size of a grapefruit. Its surface temperature is approximately 3,200 degrees Kelvin, and compared to the Sun's 5,800 degrees Kelvin, it glows a deep, dull red, emitting most of its energy in the infrared rather than in visible light. Its luminosity is roughly 0.003, 5 times that of the Sun, meaning it produces only about 1/300th of the Sun's light. Standing on a hypothetical planet at Earth's distance from Barnard's star, you would receive less than 0.5% of the sunlight we enjoy. The star would appear as a dim, ruddy disk in the sky, casting a perpetual twilight. It is cool, dim, and old. Estimates of its age range from 7 to 12 billion years, making it potentially one of the oldest stars in our galactic neighborhood. It has been burning hydrogen slowly and steadily for longer than our Sun has existed, and it will continue to do so for trillions of years. Red dwarfs are the most fuel-efficient stars in the universe. They burn their hydrogen so slowly that they will outlast virtually everything else. There is a rich and sometimes controversial history of planetary claims around Barnard's star. In the 1960s and 70s, the Dutch-American astronomer Peter van der Kamp, working at Sproul Observatory in Pennsylvania, announced that he had detected the gravitational wobble of one or possibly two Jupiter-sized planets orbiting Barnard's star. His claim was based on decades of painstaking astrometric measurements, tracking the tiny shifts in the star's position caused by the gravitational tug of orbiting bodies. The discovery was celebrated. It appeared to be the first detection of extrasolar planets, but other astronomers could not reproduce the results. Eventually, it was determined that the wobble van der Kamp had measured was caused by systematic errors in his telescope, introduced when the lens was cleaned and adjusted. The planets did not exist. It was a cautionary tale about the difficulty of detecting planets around other stars and about the dangers of systematic instrumental errors. Decades later, in 2018, a team of astronomers using the radial velocity method announced the detection of a possible planet orbiting Barnard's star. The candidate planet, designated Barnard's star B, was estimated to have a minimum mass of roughly 3.2 Earth masses, placing it in the category of super-Earths. It was thought to orbit at a distance of approximately 0.4 astronomical units, with an orbital period of roughly 233 days. However, subsequent analyses cast doubt on this detection, and as of the early 2020s, the existence of Barnard's star B remains disputed. Some studies suggest the signal may have been produced by stellar activity rather than a genuine planet. The question of whether Barnard's star hosts planets remains tantalizingly open. Regardless of whether it has planets, Barnard's star is scientifically important. Its proximity, its high proper motion, and its well-studied characteristics make it an ideal target for studies of stellar physics, astrometry, and, in the minds of dreamers, interstellar travel. It is the second closest stellar system to the Sun, after Alpha Centauri, and it is alone. Unlike Alpha Centauri, which is a triple star system consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, Barnard's star is a solitary red dwarf. There is a certain poetic loneliness in that. A dim, ancient star, travelling alone through the galaxy, heading toward us at 110 kilometers per second, destined to pass within 3.8 light-years of the Sun in roughly 10,000 years before continuing on its way. It will be the closest star to our Sun for a few thousand years, and then it will recede again, carried onward by its own momentum through the spiral arms of the Milky Way. A brief cosmic encounter, a passing neighbour who never stays. Its proper motion, that rapid drift across the sky first noticed by Barnard, reveals something fundamental about the dynamic nature of our stellar neighbourhood. Stars are not fixed, they move. They orbit the centre of the galaxy, each on its own trajectory, influenced by gravitational interactions with other stars, molecular clouds, and the galaxy's overall mass distribution. The Sun itself is orbiting the galactic centre at roughly 220 kilometers per second, completing one orbit roughly every 225 million years. Barnard's star moves on a different orbit, a steeper, more inclined path that carries it through our neighbourhood at a high velocity relative to the Sun. It is a cosmic wanderer, an old star from an earlier era of the galaxy, passing through our quiet suburb on its way to somewhere else. Now let us talk about the space between here and there. 6 light-years. The phrase rolls off the tongue easily, but the reality it describes is staggering. A light-year is the distance that light, travelling at 299,792 kilometers per second, covers in 1 year. That works out to roughly 9.46 trillion kilometers per light-year. 6 light-years is therefore approximately 56.8 trillion kilometers. Let us try to feel that number. If you laid 1 meter sticks end to end from here to Barnard's star, you would need roughly 56.8 quadrillion of them. 56.8 followed by 15 zeros. If every human being on Earth, all 8 billion of us, began laying sticks at a rate of 1 per second, working 24 hours a day without rest, it would take roughly 225 years to lay enough sticks to reach Barnard's star. 2 centuries of the entire human race, doing nothing but placing meter sticks in a line, and even then, only if we ignore the fact that you cannot lay sticks across a vacuum. Here is another way to feel the distance. The International Space Station orbits the Earth at an altitude of roughly 400 kilometers. If you could stack international space stations on top of each other from Earth to Barnard's star, you would need roughly 142 trillion of them. The total cost of building the ISS was approximately $150 billion. To build 142 trillion space stations would cost roughly $21 trillion. The entire gross domestic product of planet Earth is roughly $100 trillion per year. It would take the combined economic output of the entire planet, dedicated to nothing else, roughly 210 billion years, to produce enough wealth to build the required number of stations. The universe itself is only 13.8 billion years old. These comparisons are not meant to be whimsical. They are meant to break through the numbness that large numbers induce. When someone says 6 light years, the brain processes it as a label, not a distance. The brain files it in the same category as the distance to the grocery store, just with a different unit. But 6 light years is not in the same category as anything in human experience. It is a distance that makes a mockery of human scale, human time, and human ambition. Let us try one more comparison. If you shrank the distance between the Earth and the Moon down to the width of a human hair, roughly 1/10 of a millimeter, then the distance from Earth to Barnard's star would be approximately 148 meters. A human hair to a football pitch, and the Moon is the farthest any human being has ever traveled. We have crossed the width of a human hair, and we need to cross a football pitch. That is the ratio. That is what 6 light years means in human terms. Consider also the scale of time involved. If you compressed the entire 4.6 billion year history of our solar system into a single 24-hour day, the entire history of human civilization, from the invention of agriculture to the present, would occupy the last fraction of a second, less than 1/100th of a second. In that cosmic blink, we have gone from stone tools to spacecraft, but the time required to reach Barnard's star with current technology, roughly 100,000 years, would occupy about 2 full seconds in this compressed day, 2 seconds against a day. It sounds brief, but those 2 seconds represent a duration longer than the entire existence of organized human society we have. We have not demonstrated the capacity to maintain any coherent endeavor for even a small fraction of that timescale. Now let us consider what fills that distance. The interstellar medium is not truly empty. It is filled with an extraordinarily thin gas, primarily hydrogen and helium, with trace amounts of heavier elements, molecules, and dust grains. The average density of the interstellar medium in our region of the galaxy, called the local bubble, is actually lower than the galactic average because our solar system happens to sit inside an enormous cavity blown out by ancient supernova explosions, a region where the gas has been swept away, leaving behind an even more tenuous void than usual. The average density of the interstellar medium in the local bubble is roughly 0.05 to 0.3 atoms per cubic centimeter. Outside the local bubble, in denser regions of the galactic disk, densities can reach 1 to 10 atoms per cubic centimeter, and in molecular clouds, where new stars form, densities can exceed 1,000 atoms per cubic centimeter. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. 25, followed by 18 zeros. The interstellar medium, even at its densest in our neighborhood, is roughly 25 quintillion times less dense than air at sea level. It is, by any practical standard, a vacuum more perfect than anything we can create in a laboratory on Earth. But it is not nothing, and at the speeds required for interstellar travel, even this near-perfect vacuum becomes a serious hazard. If a spacecraft were traveling at 10% of the sea speed of light, roughly 30,000 kilometers per second, each hydrogen atom it struck would carry the kinetic energy of a small bullet. At that speed, the spacecraft would be impacting approximately 100 quadrillion atoms per square meter of frontal area per second. The cumulative effect would be a continuous bombardment of radiation and particle impacts that would erode the spacecraft's surface, heat its forward-facing structures, and deliver a potentially lethal dose of radiation to anything inside. This is not a speculative concern. It is a calculated inevitability. At 1% of the speed of light, roughly 3,000 kilometers per second, the problem is manageable but non-trivial. At 10%, it becomes serious. At 50% of the speed of light, the kinetic energy of each impacting hydrogen atom reaches the range of nuclear particle collisions. The spacecraft's forward surface would be subjected to the equivalent of a continuous particle beam. The radiation generated by these impacts would be intense enough to kill any biological organism within seconds, even behind substantial shielding. And then there is the dust. Interstellar space contains microscopic grains of silicate and carbonaceous material, typically ranging from a few nanometers to a few micrometers in size. These grains are sparse, roughly 1 grain per 100,000 cubic meters in the denser regions of the interstellar medium. But at relativistic speeds, a collision with a single dust grain would release energy comparable to a small bomb. A grain of silicate dust 1 micrometer in diameter, impacting at 10% of the speed of light, would release roughly 15 megajoules of energy, equivalent to about 3.6 kilograms of TNT. At 50% of the speed of light, the same grain would release roughly 375 megajoules, equivalent to about 90 kilograms of TNT. A spacecraft traveling at these speeds through the interstellar medium would be running a gauntlet of microscopic explosions, any one of which could punch through a hull, damage critical systems, or destroy the vessel entirely. The interstellar medium also contains magnetic fields, typically a few microgas in strength, which thread through the gas and influence the behavior of charged particles. These fields are tangled, turbulent, and complex, shaped by the movements of gas, the explosions of supernovae, and the rotation of the galaxy itself. They do not pose a direct structural threat to a spacecraft, but they influence the distribution and energy of charged particles in the medium, contributing to the overall radiation environment. Cosmic rays, high-energy protons, and atomic nuclei accelerated by supernova remnants and other astrophysical sources permeate the galaxy. On Earth, we are shielded from most cosmic rays by the planet's magnetic field and its atmosphere, which together reduce the cosmic ray flux at the surface by a factor of roughly 1,000. In deep space, this shielding is absent. The flux of galactic cosmic rays in the interstellar medium is roughly 3 to 4 particles per square centimeter per second, each one carrying enormous energy ranging from millions to trillions of electron volts. Some cosmic rays carry as much energy as a baseball thrown at highway speed, concentrated into a single subatomic particle. Over the decades or centuries required for an interstellar journey, even at high speeds, the cumulative radiation dose from cosmic rays would pose a serious threat to both electronic systems and biological passengers. Microchips are vulnerable to single-event upsets, in which a single cosmic ray strike flips a bit in a computer's memory or disrupts a transistor's operation. Over decades, these events would accumulate, degrading the reliability of onboard computers. Shielding against galactic cosmic rays is notoriously difficult because many cosmic rays are so energetic that they simply pass through conventional shielding materials. Worse, when a high-energy cosmic ray strikes a thick shield, it produces a shower of secondary particles, including neutrons and pions, which can be even more damaging than the original cosmic ray. Adding more shielding can actually increase the radiation dose to the interior of the spacecraft, a counterintuitive result that has been confirmed by extensive simulations and experiments. There is also the heliopause to consider. Our solar system is enclosed within a protective bubble called the heliosphere. Inflated by the solar wind, the continuous outflow of charged particles from the Sun. The heliosphere shields the inner solar system from much of the interstellar medium's gas and radiation. The boundary of the heliosphere, the heliopause, sits roughly 120 to 140 astronomical units from the Sun. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Beyond the heliopause, conditions change. The density of the interstellar medium increases. The radiation environment shifts. The spacecraft is no longer sheltered by the Sun's magnetic influence. Any interstellar mission would need to contend with these changed conditions for the overwhelming majority of its journey. So the space between here and Barnard's star is not empty. It is a hostile environment, thin enough to be called a vacuum, but energetic enough to destroy anything that tries to cross it too quickly. This is the first layer of the problem. The distance is not just vast, it is dangerous. The void is not passive. It is actively hostile to anything that dares to cross it at speed. The history of human exploration offers a tempting but misleading parallel. We crossed the Atlantic Ocean, we reached the poles, we climbed Everest, we walked on the moon. Each of these achievements seemed impossible before it was accomplished, and each one expanded our sense of what humanity could do. Surely, the argument goes, interstellar travel is simply the next step in this grand tradition of overcoming the impossible. But this analogy fails at a fundamental level. Every previous frontier we have crossed has existed within the same basic physical environment. The Atlantic Ocean is made of water. The poles are covered in ice. The moon is a rocky body orbiting the Earth at a distance that light crosses in 1.3 seconds. All of these environments, however challenging, operate within the regime of Newtonian physics, of chemical energy, of human timescales. The journey times were days, months, or at most a few days in the case of the moon. The energy requirements were large but achievable with the technology of the era. Interstellar space is different in kind, not just in degree. The distances are not thousands or millions of times greater than previous frontiers. They are billions of times greater. The energy requirements are not challenging. They are beyond the output of entire civilizations. The journey times are not months or years. They are millennia or tens of millennia. And the physics that governs the situation, special relativity and the rocket equation, places hard limits that no technology can circumvent. This is not the next step in a grand tradition of exploration. It is a different category of problem entirely, governed by different rules, operating at different scales, and constrained by different physics. The question is not whether we want to reach Barnard's star. The question is whether the universe will let us. And the answer, as we will see, is far more complicated and far more sobering than most popular science suggests. Now let us establish some basic physics that governs how fast we can travel and how much energy it takes to do so. This is where the problem shifts from engineering to fundamental physics, and where the true barriers begin to emerge. The speed of light, roughly 300,000 kilometers per second, is the absolute speed limit of the universe. Nothing with mass can reach it. This is not an engineering limitation. It is a structural feature of spacetime, embedded in Einstein's special theory of relativity published in 1905. As an object with mass accelerates toward the speed of light, its relativistic mass increases. The energy required to accelerate it further grows without bound. To accelerate even a single kilogram to the speed of light would require an infinite amount of energy. This is not a practical barrier that better technology might overcome. It is a mathematical impossibility, a wall built into the equations that describe reality. At speeds well below the speed of light, Newtonian mechanics works fine. The energy required to accelerate an object is proportional to the square of its velocity. Double the speed, quadruple the energy. But as you approach a significant fraction of the speed of light, relativistic effects take over, and the energy requirements grow far more steeply. At 90% of the speed of light, the relativistic kinetic energy of a 1 kilogram object is roughly 1.3 times 10 to the 17th joules. That is equivalent to the energy released by roughly 30 million tons of TNT, or about 2,000 Hiroshima-sized nuclear bombs, for a single kilogram. A spacecraft weighing 100,000 kilograms, roughly the mass of a large unmanned probe, would require 10 to the 22nd joules to reach 90% of the speed of light. That is roughly the total energy output of the Sun over an entire second. For a single spacecraft, these numbers are not negotiable. They are not the result of inefficient engines or primitive technology. They are the direct consequence of the relationship between mass, velocity, and energy, as described by special relativity. The equation is E equals gamma minus 1 times m times c squared, where gamma is the Lorentz factor and c is the speed of light. No engineering breakthrough can change this equation. No future technology can reduce the energy required. The cost of speed is fixed by the universe itself. If the Sun were the size of a basketball, roughly 24 centimeters in diameter, the Earth would be a tiny bead about 2 millimeters across, sitting 26 meters away, and Barnard's star would be another ball, smaller and dimmer, sitting roughly 40,000 kilometers away. That is approximately the circumference of the Earth. Two small balls, one in your hand and one on the opposite side of the planet, and the space between them is filled with nothing but vacuum, radiation, and dust. That is the scale of the challenge. If you compress the entire journey from Earth to Barnard's star into a single day, making the 57 trillion kilometers pass in 24 hours, you would need to travel at roughly 659 billion kilometers per hour. That is about 2,200 times the speed of light. And the speed of light is the maximum. You cannot travel 2,200 times faster than the speed limit. The scale compression reveals the absurdity. The distance is so vast relative to the maximum speed that even wildly generous assumptions about technology cannot close the gap in any human-relevant timeframe. Let us now consider the journey in terms of human lifespan. The average human life expectancy is roughly 75 years. If you wanted to reach Barnard's star within a single human lifetime, say 50 years of travel, you would need to maintain an average speed of roughly 11% of the speed of light, or about 33,000 kilometers per second. That is more than 1,900 times faster than any spacecraft we have ever built. Let us cascade through our speed milestones to feel this gap. A commercial airplane flies at roughly 900 kilometers per hour. A bullet travels at roughly 1,200 meters per second. The International Space Station orbits at roughly 7.7 kilometers per second. The Apollo spacecraft reached roughly 11 kilometers per second on the way to the Moon. The Parker Solar Probe reaches 176 kilometers per second during its closest solar passes, and the speed needed for a 50-year journey to Barnard's star is 33,000 kilometers per second. That is roughly 188 times faster than the Parker Solar Probe, which is itself thousands of times faster than a car. The gap between our best speed and the required speed is not a gap that incremental improvement can close. It is a chasm that separates two entirely different regimes of physics. The energy required to accelerate a modest spacecraft to that speed would exceed the annual energy output of the entire human civilization by many orders of magnitude. And this calculation ignores the energy needed to decelerate at the destination, which would roughly double the total requirement. It also ignores the mass of the fuel itself, which creates a vicious feedback loop known as the tyranny of the rocket equation. The tyranny of the rocket equation, first described mathematically by the Russian scientist Konstantin Tsiolkovsky in 1897, is one of the most fundamental constraints on space travel. It states that the velocity change a rocket can achieve is determined by the exhaust velocity of its propellant and the ratio of the rocket's initial mass to its final mass. To achieve a high velocity change, a rocket must carry a large amount of fuel, but carrying more fuel adds mass, which requires even more fuel to accelerate. The relationship is exponential, not linear. To double the velocity change, you do not double the fuel. You square the fuel ratio. To triple it, you cube it. For the velocities required for interstellar travel, the fuel requirements become absurd, then impossible, then mathematically infinite. For a chemical rocket with an exhaust velocity of roughly 4.5 kilometers per second, the fuel-to-payload ratio required to reach even 1% of the speed of light is approximately 10 to the 291st power to 1. That number has 291 digits. It is larger than the number of atoms in the observable universe, which is roughly 10 to the 80th power. You would need more fuel than there are atoms in the cosmos. Chemical rockets are fundamentally, categorically incapable of interstellar travel. They are not even in the conversation. Nuclear thermal rockets, with exhaust velocities of roughly 9 kilometers per second, do slightly better. Ion drives, with exhaust velocities of 30 to 50 kilometers per second, do better still. But even the most advanced propulsion concepts, such as nuclear pulse propulsion or antimatter drives, face the same exponential tyranny. The fuel requirements grow without mercy as the target velocity increases. The rocket equation is not a problem to be solved. It is a law of nature to be obeyed. This brings us back to Barnard's star. 6 light-years away, roughly 57 trillion kilometers, the nearest solar star to our Sun. It has been studied, measured, analyzed, and dreamed about for over a century, and every serious analysis of how to reach it has concluded the same thing. The energy requirements are staggering. The timescales are enormous. The engineering challenges are beyond anything we can currently achieve. And the physics itself, the basic relationship between mass, velocity, and energy, places hard limits that no amount of ingenuity can circumvent. Then something happened that changed the way scientists thought about interstellar travel. Not a breakthrough, not a discovery, an accumulation of calculations, each one more dispiriting than the last, each one narrowing the window of possibility, each one revealing another constraint, another barrier, another way in which the universe has made the stars unreachable. The picture that emerged is not one of eventual triumph. It is one of fundamental limitation, and it begins with the most basic resource of all, energy, the currency that the universe demands for every meter of progress, the price that cannot be negotiated, cannot be reduced, cannot be waived. Energy is what separates dreams from destinations, and the universe has set the price for reaching Barnard's star at a level that would bankrupt civilizations. The core problem with reaching Barnard's star is not distance. Distance is just a number. The core problem is energy. Specifically, the grotesque, civilization-dwarfing quantity of energy required to accelerate anything to a meaningful fraction of the speed of light, sustain it across the interstellar void, and then decelerate it at the destination. This is where the dream of interstellar travel crashes into the hard wall of physics, and where every optimistic projection shatters against the immovable reality of the rocket equation. Let us begin with the most basic calculation. To reach Barnard's star in a reasonable time frame, say 50 years, a spacecraft would need to travel at roughly 11 to 12% of the speed of light. Let us round to 10% for simplicity, which gives a velocity of roughly 30,000 kilometers per second. The kinetic energy of a 100,000 kilogram spacecraft traveling at 10% of the speed of light is approximately 4.5 times 10 to the 19th joules. For context, the total energy consumption of the entire human civilization in the year 2020 was approximately 5.8 times to the 20th joules. So accelerating a single modest spacecraft to 10% of the speed of light would consume roughly 8% of the world's annual energy output. And that is just the acceleration. To stop at the destination, the spacecraft must decelerate by the same amount, which requires the same energy again. The total energy budget is now roughly 16% of global annual energy production. For a single spacecraft, with no passengers, no life support, no scientific instruments worth mentioning, just a 100,000 kilogram hunk of metal moving very fast. But this calculation is dishonestly optimistic because it ignores the most punishing constraint in all of rocketry, the fuel problem. A rocket works by throwing mass backward. The momentum of the ejected mass pushes the rocket forward. This is Newton's third law. The efficiency of this process depends on how fast the exhaust is ejected, which is measured by the specific impulse or exhaust velocity of the propulsion system. Chemical rockets eject their exhaust at roughly 4 to 5 kilometers per second. Nuclear thermal rockets can achieve roughly 9 kilometers per second. Ion drives can reach 30 to 80 kilometers per second. Nuclear pulse drives, like those envisioned in Project Orion, could potentially reach hundreds of kilometers per second. And the theoretical maximum for a matter and antimatter drive, where the exhaust is pure photons, is the speed of light itself. The rocket equation, published by Konstantin Tsiolkovsky in 1897, relates the change in velocity of a rocket, called delta V, to the exhaust velocity of its engine and the ratio of its initial mass to its final mass. The equation is deceptively simple. Delta V equals exhaust velocity multiplied by the natural logarithm of the mass ratio. But the implications are devastating. Because the natural logarithm grows slowly, achieving a large delta V requires an exponentially large mass ratio. And for interstellar velocities, the mass ratios become absurd. Consider a chemical rocket with an exhaust velocity of 4.5 kilometers per second. To achieve a delta V of 30,000 kilometers per second, roughly 10% of light speed, the mass ratio would need to be e to the power of 30,000 divided by 4.5, which is e to the power of 6,667. This number is so large that it has no physical meaning. It exceeds not just the mass of the Earth, not just the mass of the Sun, not just the mass of the Milky Way galaxy, but the mass of the entire observable universe by a factor with thousands of digits. Chemical rockets cannot reach the stars. They cannot even begin to approach the velocities needed. An ion drive with an exhaust velocity of 50 kilometers per second is better but still hopelessly inadequate. The mass ratio for 10% of light speed would be e to the power of 600, still an unimaginably large number. A nuclear pulse drive with an exhaust velocity of 1,000 kilometers per second would require a mass ratio of e to the 30, which is approximately 10 to the 13th, 13 orders of magnitude, 10 trillion to 1. To deliver 1 kilogram of payload to Barnard's star, you would need 10 trillion kilograms of nuclear bombs. That is roughly the mass of a large asteroid. For 1 kilogram of payload, it is worth pausing here to examine the most serious engineering study ever conducted for a mission to Barnard's star. Project Daedalus was a study carried out by the British Interplanetary Society between 1973 and 1978. A team of 11 volunteer engineers and scientists set out to design an unmanned interstellar probe that could reach Barnard's star within a single human lifetime. The design they produced was ambitious, detailed, and ultimately sobering. The Daedalus spacecraft was designed to use nuclear pulse propulsion, but not the crude atomic bombs of Project Orion. Instead, it would use pellets of deuterium and helium-3, ignited by powerful electron beams in a series of controlled fusion explosions. Each pellet would be injected into a combustion chamber at a rate of 250 pellets per second, each one detonating in a burst of plasma that would be directed backward by a magnetic nozzle. The engine would operate for roughly 2 years during the acceleration phase, pushing the 545 metric ton spacecraft to approximately 12% of the speed of light. The engineering specifications were daunting. The spacecraft would be roughly 190 meters long. It would carry 36,000 metric tons of helium-3 fuel, which would be mined from the atmosphere of Jupiter, a feat that itself would require technologies far beyond anything currently available. The payload, including scientific instruments, would be roughly 450 metric tons. The entire vehicle, fully fueled, would mass approximately 54,000 metric tons. The Daedalus design was for a one-way flyby. It had no means of deceleration. It would pass through the Barnard star system at 12% of light speed, collecting data for a few hours during the encounter, and then continue onward into interstellar space forever. The journey time would be approximately 50 years. The cost, in the currency of the 1970s, was not seriously estimated, but the mass of helium-3 fuel alone, 36,000 metric tons, gives some indication. Helium-3 is extraordinarily rare on Earth. The entire known terrestrial supply is measured in kilograms. Mining it from Jupiter's atmosphere would require a sustained industrial presence in the outer solar system that is centuries beyond our current capabilities. Project Daedalus demonstrated that an interstellar flyby is at least theoretically possible within the known laws of physics, but it also demonstrated the staggering scale of the enterprise. A spacecraft the size of a naval vessel, fueled by tens of thousands of tons of an element so rare on Earth that our entire supply could fit in a few containers, propelled by fusion explosions at a rate of 250 per second, and capable of nothing more than a brief flyby, with no possibility of return. A later study, Project Longshot, conducted at the United States Naval Academy in 1987 and 88, took a slightly different approach. Longshot was designed to reach Alpha Centauri rather than Barnard's star, but the physics is similar. It proposed a fission-powered spacecraft that would carry 300 metric tons of helium-3 and deuterium fuel, accelerate to roughly 4.5% of the speed of light, and make the journey in roughly 100 years. Unlike Daedalus, Longshot was designed to decelerate at the destination, entering orbit around the target star. This required a substantially larger fuel load and a longer journey, but it offered the enormous advantage of being able to study the destination system in detail rather than merely photographing it during a brief flyby. Neither Daedalus nor Longshot was ever built. Neither was ever seriously proposed for construction. They were design exercises, proof-of-concept studies meant to explore the boundaries of possibility. And what they found was a boundary that is, for now, impassable. Then there is antimatter, the most energetic fuel conceivable. When matter meets antimatter, the two annihilate completely, converting 100% of their combined mass into energy. This is the theoretical maximum, vastly exceeding nuclear fission, which converts roughly 0.1% of mass to energy, and nuclear fusion, which converts roughly 0.7%. 1 kilogram of antimatter, annihilating with 1 kilogram of matter, would release roughly 1.8 times 10 to the 17th joules, equivalent to about 43 megatons of TNT. That is roughly the energy of the largest nuclear weapon ever detonated, the Soviet Tsar bomber. An antimatter-powered spacecraft could, in principle, achieve exhaust velocities approaching the speed of light, dramatically reducing the mass ratio needed for interstellar velocities. At an exhaust velocity of even 30% of light speed, the mass ratio for a 10% light speed delta V would be roughly e to the 1/3, or about 1.4 to 1. Manageable, almost elegant, but the problem with antimatter is production. Currently, the world's entire production of antimatter, from every particle accelerator on Earth combined, amounts to roughly 10 to 20 nanograms per year. A nanogram is 1/1000th of a gram. At current production rates, it would take roughly 100 billion years to produce 1 gram of antimatter. The journey to Barnard's star would require kilograms or tons of the stuff. The production time, at current rates, would exceed the age of the universe by many orders of magnitude. And the cost. Current estimates place the price of antimatter at roughly $62.5 trillion per gram. For a 1 kilogram fuel load, the cost would be roughly $62.5 quadrillion. The gross domestic product of the entire planet is roughly $100 trillion per year. It would take 625 years of the entire world's economic output, dedicated to nothing else, to produce 1 kilogram of antimatter. Even if production rates could be increased by orders of magnitude and cost reduced by similar factors, the storage problem remains. Antimatter cannot touch matter. If it does, it annihilates instantly, with explosive force. Antiprotons are typically stored in magnetic traps, called penning traps, which use magnetic and electric fields to suspend the antiprotons in a vacuum, preventing contact with the walls of the container. Current penning traps can store a few antiprotons for weeks or months, storing kilograms of antimatter for decades, in a container that must survive the vibrations of launch, the stresses of acceleration, the radiation of deep space, and the operational demands of a 60-year mission, is a challenge that makes the production problem look simple by comparison. And even this calculation is optimistic, because it assumes a one-way trip with no deceleration. If you want to slow down at Barnard's star, the delta V doubles, the mass ratio squares. 10 trillion becomes 100 trillion, or 10 to the 26th. And if you want a round trip, the mass ratio squares again. The numbers leave the realm of engineering and enter the realm of pure absurdity. The only propulsion concept that avoids the worst of the rocket equation is the beamed energy concept, where the spacecraft does not carry its own fuel. Instead, energy is transmitted to the spacecraft from an external source, typically a laser or microwave beam fired from the home system. The spacecraft carries a large sail that absorbs the beam, converting the momentum of the photons into thrust. Because the spacecraft does not carry fuel, the mass ratio problem disappears. The spacecraft can, in principle, be accelerated to any speed the beam can deliver. This is the concept behind the Breakthrough Starshot initiative, proposed in 2016. The idea is to use a ground-based laser array with a combined power of roughly 100 gigawatts to accelerate tiny probes, each weighing only a few grams, to approximately 20% of the speed of light. At that speed, the probes could reach Proxima Centauri in about 20 years and Barnard's star in about 30 years. The concept is technically plausible, at least in broad outline, but the engineering challenges are staggering. A 100 gigawatt laser array would consume roughly 100 million kilowatt hours of energy per second of operation. The total energy needed to accelerate a 4-gram probe to 20% of light speed is approximately 7.2 times 10 to the 13th joules, which must be delivered in a burst lasting only a few minutes. While the probe is still close enough for the beam to focus effectively, the beam must be focused on a sail a few meters across over distances of millions of kilometers, requiring optical precision that is far beyond current technology, and the probes themselves would be so small, just a few grams each, that they could carry only the most rudimentary instruments, perhaps a camera, a spectrometer, and a communication laser. No life support, no ability to stop, no way to send back more than a trickle of data from a distance of 6 light-years. But here's the problem. Even if Breakthrough Starshot works perfectly, it solves only a tiny fraction of the interstellar travel challenge. It can send a few grams to the nearest stars. It cannot send anything meaningful. Not a human being, not a colony, not even a sophisticated robotic probe with the mass of a laptop computer. The laser sail concept works precisely because the payload is almost nothing. Scale the payload up to anything useful, and the energy requirements grow proportionally. A 1 kilogram probe would require roughly 250 times the energy. A 100 kilogram probe would require 25,000 times the energy. A human being, plus minimal life support, plus a capsule to contain them, might mass 10,000 kilograms. The energy required would be roughly 2.5 million times what Breakthrough Starshot envisions. That is 25 million gigawatt seconds of laser energy, equivalent to the entire electrical output of the United States for roughly 7 hours, delivered in a focused beam over the course of a few minutes. And this still does not include any means of deceleration at the destination, and it gets worse. All of these calculations assume perfectly efficient energy conversion, no waste heat, no beam divergence, no atmospheric losses, no imperfections in the sail's reflectivity. In practice, efficiencies of 50 to 70% are optimistic, which increases the energy requirements by a factor of 2 to 3. The engineering requirements for maintaining beam coherence over millions of kilometers are beyond anything we have demonstrated, and the political and economic will to build a 100 gigawatt laser array, which would be the most powerful energy weapon ever constructed, would face obstacles that go far beyond engineering. Let us set aside beamed propulsion for a moment and consider the problem from a different angle: the biological barrier. Human beings are fragile. We evolved at the bottom of an atmosphere, in a gravitational field of 1G, in a radiation environment that is heavily shielded by the Earth's magnetic field and its blanket of air. Our bodies are adapted to a very narrow range of conditions. We need oxygen at a partial pressure of roughly 21 kilopascals. We need ambient temperatures between roughly 15 and 35 degrees Celsius. We need food, water, and the ability to eliminate waste. We need protection from radiation. We need gravity, or at least some form of mechanical loading, to prevent the devastating effects of bone loss and muscle atrophy that occur in weightlessness. And we need psychological sustenance, social interaction, meaningful activity, and hope. A journey to Barnard's star at 10% of the speed of light would take roughly 60 years. At 5%, it would take roughly 120 years. At 1%, 600 years. At the speed of Voyager 1, roughly 106,000 years. None of these timescales are compatible with a single human lifespan except the first, and even 60 years of spaceflight would require an entire human life spent inside a spacecraft, from youth to old age, with no possibility of return or rescue. The biological challenges of a 60-year spaceflight are immense. The spacecraft would need to be a self-contained ecosystem, recycling air, water, and waste with near-perfect efficiency for 6 decades. Current life support systems on the International Space Station recycle roughly 90% of water and a lower fraction of air, and they require regular resupply from Earth. A spacecraft 6 light-years from home could not be resupplied. Any failure in the life support system could be fatal, and over 60 years, failures are not just possible, they are certain. Radiation is perhaps the most intractable biological problem. In deep interstellar space, the crew would be exposed to galactic cosmic rays continuously for 60 years. The cumulative radiation dose would be enormous. Current estimates suggest that a round trip to Mars, which takes roughly 2 to 3 years, would expose astronauts to roughly 1 sievert of radiation, which is associated with a roughly 5% increase in lifetime cancer risk. A 60-year journey through interstellar space, with minimal shielding, could deliver tens or even hundreds of sieverts, a dose that would cause acute radiation syndrome, organ damage, and almost certain death. Shielding against galactic cosmic rays is extremely difficult because they are extremely energetic, and as discussed earlier, thick shielding can produce dangerous secondary particles. The psychological challenges are equally daunting. Human beings are social creatures. We need community, novelty, purpose, and the sense that our actions have consequences. A crew of astronauts locked inside a spacecraft for 60 years, with no possibility of contact with Earth except through time-delayed radio signals, with no new people, no new environments, no possibility of escape, would face psychological pressures that no human society has ever encountered. Studies of isolated communities, submarine crews, Antarctic research stations, and long-duration ISS missions have all documented the psychological toll of confinement, isolation, and monotony. These studies typically involve periods of months to a year or two. The interstellar scenario involves decades, the entire adult lives of the crew. Their children, if they have any, would be born, raised, and die inside the spacecraft, never knowing any other world. Then there is the generation ship concept. If a single human lifespan is too short for the journey, perhaps the journey could span multiple generations. A large spacecraft, carrying a community of hundreds or thousands of people, could maintain a population across the centuries required for a slow interstellar crossing. Children would be born on the ship, grow up, have children of their own, grow old, and die, all while the ship drifts through the void. After dozens or hundreds of generations, the descendants of the original crew would arrive at the destination. This concept has been explored extensively in science fiction and, to a lesser extent, in engineering studies. The challenges are formidable. The ship would need to be enormous, large enough to sustain a genetically viable population for centuries or millennia. Estimates of the minimum viable population for a generation ship range from a few hundred to several thousand individuals, depending on assumptions about genetic diversity, birth rates, and the tolerance for inbreeding. The ship would need to be a self-sustaining ecosystem with near-zero waste, capable of producing food, recycling all materials, and maintaining all mechanical and electronic systems without external resupply for thousands of years. No human-made machine has ever operated continuously for more than a few decades without significant maintenance and refurbishment. The oldest continuously operating machines are things like tower clocks and simple water mills, mechanical devices with few moving parts. Complex machines, the kind required for life support, navigation, power generation, and communication, have much shorter operational lifetimes. The International Space Station requires constant maintenance and resupply, and it has been in orbit for only about 25 years. Its systems are regularly replaced and upgraded by visiting crews and cargo missions. A generation ship would need to operate for 1,000 times longer, with infinitely more complexity, zero external maintenance, and no possibility of resupply. Every seal would need to last millennia. Every circuit board, every pump, every bearing, every cable would need to function flawlessly or be replaceable from onboard stocks for longer than any human institution has ever existed. Consider what 1,000 years means in terms of material degradation. Metals corrode. Plastics degrade under radiation. Lubricants dry out. Seals crack. Circuits develop shorts. Even in the most benign conditions, materials have finite lifetimes. In the radiation-intense, vacuum-extreme environment of interstellar space, those lifetimes are often shorter. A generation ship would need materials that can withstand 1,000 years of radiation exposure, thermal cycling, and mechanical stress or it would need the ability to manufacture replacement components from raw materials carried on board, which implies an entire industrial base contained within the ship. There is also the social challenge, and it is perhaps the most intractable of all. No human society has ever maintained political stability, cultural continuity, and technological competence across more than a few centuries, and most have collapsed or transformed beyond recognition within a few generations. The Roman Empire lasted roughly 500 years in the West, longer in the East, and it underwent profound transformations during that time. The longest-lived human institutions, certain religious orders and universities, have persisted for roughly a millennium, but they have done so within the context of larger, changing societies that sustained them. A generation ship society would have no external society. It would be entirely self-contained. Every social pathology, every conflict, every failure of governance, every loss of knowledge would have to be resolved internally, with no safety net and no possibility of outside intervention. History suggests that isolated, confined communities tend toward dysfunction. Studies of closed communities, intentional communes, isolated settlements, and long-duration submarine deployments have documented patterns of social breakdown, power struggles, depression, and loss of motivation. These studies typically involve populations of dozens to hundreds over periods of months to years. The generation ship scenario involves populations of thousands over periods of centuries. The social dynamics are largely unknown, and the stakes are absolute. A social collapse on a generation ship would not merely end the mission, it would end the society. There is no lifeboat, there is no shore to swim to. A crew that arrives at Barnard's Star after a 1,000-year voyage might have no connection to, no understanding of, and no interest in the mission that launched them. They might have developed an entirely new culture, new language, new values. They might have forgotten why they are on the ship. They might have decided, generations ago, that the mission was pointless, or that the destination was a myth, or that the ship itself was the entire universe. The generation ship solves the biological problem of lifespan by distributing the journey across many lives. But it creates a civilizational problem that may be even harder to solve. Something is wrong with our assumptions. We assume that the problem of interstellar travel is primarily a problem of propulsion, of finding a fast enough engine, but the problem is far more multifaceted than that. It is a problem of energy, of biology, of engineering, of sociology, and of time. Each of these dimensions imposes its own constraints, and the constraints compound. A fast enough engine still requires enough energy. A fast enough trip still exposes the crew to radiation. A ship that lasts long enough still requires a society that can maintain it. Every solution to one problem creates or reveals another. The challenges do not line up politely for resolution. They interact, interfere, and amplify. And there is a further constraint that we have not yet discussed: the deceleration problem. Getting to Barnard's Star is only half the challenge. The other half is stopping. And stopping, it turns out, may be the harder half. If a spacecraft accelerates to 10% of the speed of light, it must then decelerate by the same amount to arrive at Barnard's Star at a speed that allows it to enter orbit or study the system in any meaningful way. Without deceleration, the spacecraft would flash through the Barnard Star system in a matter of hours, traveling at 30,000 kilometers per second. At that speed, the entire system, from the star's immediate vicinity to the orbit of any possible planets, would be traversed in minutes. Spacecraft's instruments would have a brief window, perhaps a few hours, to collect data before the star receded into the distance behind it. This is better than nothing, but it is not exploration. It is a snapshot taken from a speeding train. Deceleration requires the same delta V as acceleration. This is an inescapable consequence of Newton's laws. To slow down from 30,000 kilometers per second to zero, relative to the destination, requires 30,000 kilometers per second of delta V. If the spacecraft is using onboard fuel, this delta V must be provided by the engine, which means the spacecraft must carry enough fuel for both the acceleration and the deceleration. And here is where the rocket equation becomes truly murderous. For a rocket, the fuel for deceleration must be carried during the acceleration phase. This means it is part of the initial mass. The fuel to accelerate the deceleration fuel must also be carried, and the fuel to accelerate that fuel The mass ratio does not merely double, it squares. If acceleration alone requires a mass ratio of 10,000 to 1, then acceleration plus deceleration requires a mass ratio of 100 million to 1. The exponential nature of the rocket equation turns a difficult problem into an impossible one. Some proposals attempt to avoid this problem by using the destination star itself for braking. A spacecraft with a large magnetic sail could potentially use the stellar wind from Barnard's star to decelerate. But the stellar wind from a red dwarf is much weaker than the solar wind from a star like our Sun, and the braking force available is tiny compared to the momentum of a spacecraft traveling at 10% of light speed. Calculations suggest that magnetic braking could reduce the spacecraft's speed by a few kilometers per second, perhaps tens of kilometers per second, but not by the tens of thousands of kilometers per second needed. The destination star cannot help us stop. We must carry our braking fuel with us. Another proposal involves using a light sail deployed at the destination. If the spacecraft carries a large reflective sail, the light from Barnard's star could provide a braking force. But Barnard's star produces only 1/300th of the Sun's luminosity. The radiation pressure available is correspondingly tiny. A sail large enough to decelerate a meaningful payload from 10% of light speed using Barnard's star's feeble light would need to be hundreds or thousands of kilometers across, far larger than any structure humanity has ever built, and the deceleration time would be measured in decades or centuries, during which the spacecraft would overshoot the target system by a vast distance. The deceleration problem is not a footnote. It is central to the entire enterprise. Without a solution to deceleration, every interstellar mission is a flyby. Flybys are scientifically valuable, but they are not colonization, they are not settlement, they are not even thorough exploration. They are drive-by photography at cosmic velocities. If we are serious about reaching Barnard's star, about arriving, about studying, about staying, then the deceleration problem must be solved. And no known solution works within the constraints of current or foreseeable physics. There is one more physical constraint worth examining in detail: the waste heat problem. Any propulsion system that converts energy into thrust also produces waste heat, and the thermodynamic efficiency of the conversion is never 100%. At the power levels required for interstellar travel, the waste heat is enormous, and managing it becomes a dominant engineering challenge. A nuclear pulse drive detonating fusion pellets at a rate of 250 per second, as Daedalus envisioned, would produce thermal loads measured in terawatts. The magnetic nozzle and the pusher structures would need to absorb, conduct, and radiate heat at rates that would challenge any known material. Tungsten, one of the most heat-resistant metals, melts at 3,687 degrees Kelvin. Carbon-carbon composites can withstand higher temperatures, but are brittle and vulnerable to erosion. The temperatures inside the combustion chamber of a fusion pulse drive would exceed 100 million degrees Kelvin. Only magnetic confinement, keeping the plasma from touching any physical structure, can make this workable. And magnetic confinement at these scales, sustained for years of continuous operation, is far beyond anything we have demonstrated. An antimatter drive would be even worse. When protons and antiprotons annihilate, roughly 30% of the energy goes into charged pions, which can be directed magnetically. The remaining 70% goes into neutral pions, which immediately decay into gamma rays. These gamma rays cannot be magnetically directed. They radiate in all directions, passing through shielding, depositing energy in the spacecraft's structure, and delivering lethal radiation doses to any nearby biological matter. An antimatter drive is simultaneously the most efficient and the most dangerous propulsion concept ever conceived. It converts mass to energy with perfect efficiency and then distributes a large fraction of that energy as lethal radiation in all directions. Managing waste heat is one of the most underappreciated challenges in spacecraft design. In the vacuum of space, there is no air to carry heat away through convection. The only mechanism for heat dissipation is radiation, governed by the Stefan-Boltzmann law. The rate of radiative cooling is proportional to the surface area of the radiator. multiplied by the fourth power of the absolute temperature. To radiate a terawatt of waste heat at a radiator temperature of 1000 degrees Kelvin would require a radiator surface area of roughly 17 million square meters, equivalent to a square roughly 4 kilometers on each side. Carrying such a radiator, with its structural mass and supporting systems, would add thousands or tens of thousands of metric tons to the spacecraft, further compounding the fuel problem. And then there is the communication problem, often overlooked but critical. A spacecraft at Barnard's star would be 6 light-years from Earth. Any radio or laser signal would take 6 years to travel each way. A conversation would have a 12-year round-trip delay. Mission controllers on Earth could not provide real-time guidance. Any emergency would need to be resolved on board, with no possibility of help from home. The spacecraft would need to be fully autonomous, capable of diagnosing and repairing any problem without human intervention for the entire duration of the mission. Current artificial intelligence and robotic systems are nowhere near this level of capability. They might be someday, but the timeline for achieving fully autonomous, self-repairing, self-directing robotic intelligence is measured in decades at minimum, and the reliability requirements for a 60-year mission with no external support are orders of magnitude beyond anything we have demonstrated. There is also the navigation problem. In interstellar space, there are no landmarks, no GPS satellites, no ground stations. The spacecraft must determine its position and velocity using onboard instruments, likely by observing the positions of known stars and comparing them to a star catalogue. This requires extremely precise optical instruments and the ability to compensate for the spacecraft's own velocity, which causes stellar aberration, the apparent shift in star positions caused by the observer's motion. At 10% of the speed of light, the aberration is significant, distorting the apparent positions of stars by several degrees. The navigation system must be able to measure star positions with sub-arcsecond precision and account for these relativistic effects over decades of continuous operation, without calibration from any external source. But here's what makes this truly terrifying. Every one of these constraints, the energy requirement, the rocket equation, the radiation environment, the biological limits, the deceleration problem, the waste heat, the communication delay, the navigation challenge, operate simultaneously. They do not wait politely in line to be solved one at a time. They interact. They amplify each other. Solving the energy problem by using a more powerful engine creates a worse waste heat problem. Solving the radiation problem by adding shielding increases the mass, which worsens the fuel problem. Extending the journey time to reduce the speed requirement creates worse biological, engineering, and sociological problems. Shortening the journey time to address the biological problem requires more speed, which requires more energy, which requires more fuel, which requires more mass, which requires more energy. The constraints are coupled, and their coupling creates a fortress of impossibility that no single breakthrough can breach. The question is not whether any one of these problems is solvable in isolation. Individually, most of them probably are, given unlimited resources, unlimited time, and unlimited willingness to accept risk. The energy problem can be addressed with more powerful reactors. The radiation problem can be addressed with better shielding. The biological problem can be addressed with better life support. The deceleration problem can be addressed with more fuel. But each solution comes with a cost, and that cost is almost always mass. More fuel means more mass. More shielding means more mass. More life support means more mass. More deceleration capability means more mass. And more mass means more fuel to accelerate it, which means more mass, which means more fuel. The tyranny of the rocket equation ensures that every kilogram of solution requires kilograms of additional fuel, and those kilograms require kilograms of their own. The interstellar travel problem is not a single wall to be scaled. It is a web of interlocking constraints, each one connected to the others, each one reinforced by the others. Breaking through one wall only reveals another behind it. Solving one problem only deepens another. The picture that emerges from decades of serious study is not a picture of challenges waiting to be overcome. It is a picture of fundamental limits imposed by the laws of physics that constrain what is possible regardless of technology, regardless of time, regardless of ambition. This is not the same as saying interstellar travel is impossible. It is saying that reaching Barnard's star is so difficult, so constrained by so many simultaneous requirements, that it represents a challenge of a fundamentally different character than any we have ever faced. It is not the next Apollo program. It is not the next Manhattan Project. It is not even the next century's great engineering challenge. It is a problem that may require civilizational resources we do not possess, operating over timescales we cannot sustain, against physical constraints we cannot circumvent. And the answer, based on every serious study conducted to date, is that all of these problems are not solvable simultaneously within the same spacecraft, on the same mission, with the same budget of mass, energy, and time. Not with current technology, not with any technology on the foreseeable horizon, and possibly not with any technology that obeys the known laws of physics. This is the core problem, not distance, not speed, not any single constraint. The core problem is the convergence of constraints, the simultaneity of barriers, the fact that the universe has placed not one wall between us and Barnard's star, but a labyrinth of interlocking walls, each one harder to breach than the last, each one making the others harder to breach. It is a problem that humbles ambition, that resists optimism, that confronts us with the possibility that some things may be beyond the reach of any civilization, no matter how advanced. Despite the overwhelming constraints we have outlined, serious scientists and engineers have spent decades exploring potential approaches to interstellar travel. Each approach addresses some of the constraints. None addresses all of them. Let us examine 5 different strategies that have been proposed for reaching Barnard's star, and understand, for each one, exactly where and how it fails. The first approach is the slow ship. Accept that the journey will take thousands of years, and design accordingly. Do not try to go fast. Instead, go reliably. Build a massive, self-sustaining spacecraft, a generation ship, and let time do the work that speed cannot. The concept of the generation ship has been explored in science fiction and serious engineering studies since at least the 1920s. The physicist Robert Goddard, one of the pioneers of modern rocketry, wrote about the idea in his private journals as early as 1918. The concept is straightforward. Build a ship large enough to sustain a community of people for many centuries. Launch it at a modest speed, perhaps 1 to 5% of the speed of light. Let the passengers live, reproduce, and die on board, passing the mission from generation to generation until the descendants of the original crew arrive at the destination. At 1% of the speed of light, roughly 3,000 kilometers per second, the journey to Barnard's star would take approximately 600 years. At 5%, roughly 120 years. These are long timescales, but they are not geological. They are comparable to the lifespan of major human institutions. The Roman Republic lasted roughly 500 years. The Ottoman Empire lasted roughly 600 years. The Catholic Church has persisted for roughly 2,000 years. Perhaps, the argument goes, a spacecraft community could maintain coherence for a comparable period. The engineering requirements are staggering, but not obviously impossible. The ship would need to be large, likely kilometers in length and hundreds of meters in diameter, to provide enough space for agriculture, living quarters, recreational areas, and industrial facilities. Estimates of the minimum viable crew size range from 500 to 10,000 people, depending on assumptions about genetic diversity, specialization of labor, and psychological health. The total mass of the ship, including structure, crew, supplies, and propulsion, would likely be in the hundreds of thousands to millions of metric tons. The agricultural requirements alone are daunting. A population of several thousand people would need roughly 2,000 to 3,000 calories per person per day, requiring the cultivation of crops, the raising of livestock, or growth of cultured protein, and the processing and distribution of food. This would need to be done in enclosed, artificially lit greenhouses, using recycled water and nutrients, with no margin for crop failure. On Earth, agriculture is supported by an entire biosphere, by weather systems, by soil microbiomes, by pollinators, by the cycling of nutrients through ecosystems that evolved over billions of years. A generation ship would need to replicate the essential functions of these systems artificially, in a closed loop, for centuries. The Biosphere 2 experiment in Arizona, which attempted to create a self-sustaining enclosed ecosystem in the 1990s, struggled dramatically with atmospheric regulation, food production, and ecosystem stability, and it was abandoned as a self-sustaining system after only 2 years. The challenges of maintaining a closed ecosystem for 600 years at the scale needed to feed thousands of people are not just difficult. They are orders of magnitude beyond anything we have demonstrated. Several design concepts have been proposed. The Stanford Torus, designed during a NASA summer study in 1975, envisioned a rotating wheel-shaped habitat roughly 1.8 kilometers in diameter, housing approximately 10,000 residents. It was designed as an orbital habitat, not an interstellar vessel, but the basic principles of rotation for artificial gravity, enclosed ecosystem management, and self-sufficient community design apply equally to generation ships. The Island 3 concept, proposed by physicist Gerard O'Neill in 1974, described cylindrical habitats up to 32 kilometers long and 6.4 kilometers in diameter, housing millions of people. Scaled down and equipped with propulsion, these designs could form the basis of a generation ship. But even the most detailed designs remain conceptual. No prototype has been built. No enclosed ecosystem has demonstrated long-term stability. The generation ship remains a thought experiment, not a blueprint, but the limitations of the slow ship approach are severe. First, propulsion. Even at 1% of light speed, the energy requirements are enormous. A 1 million metric ton ship traveling at 1% of light speed has a kinetic energy of roughly 4.5 times 10 to the 22nd joules, equivalent to the annual energy output of the Sun for roughly 1/10 of a second. This energy must be generated by the ship's propulsion system, which must also carry its own fuel, invoking once again the tyranny of the rocket equation. Second, reliability. A 600-year journey requires every critical system, propulsion, life support, power generation, structural integrity, to function reliably for 6 centuries. As discussed in the previous section, no human-made machine has ever achieved this. The maintenance requirements over 600 years would be continuous and demanding. The ship would need a complete manufacturing capability, the ability to fabricate replacement parts from raw materials, which implies mining, refining, machining, and assembly facilities on board. The ship is not a vehicle, it is a civilization. Third, social stability. 600 years of continuous isolated community life, with no external contact, no immigration, no cultural exchange, and no possibility of escape. The social dynamics of such a community are unknown and potentially catastrophic. Internal conflicts, power struggles, cultural drift, loss of knowledge, loss of motivation. All of these are realistic threats that no design study has adequately addressed. Consider what has happened on Earth over any 600-year period. 600 years ago, it was roughly 1426. The Ottoman Empire was expanding. The Chinese Ming dynasty was building the Forbidden City. Europe was emerging from the medieval period into the Renaissance. The printing press had not yet been invented. The Americas had not yet been contacted by Europeans. The scientific revolution, the industrial revolution, the digital revolution, none of these had occurred. The world of 1426 would be unrecognizable to a person from the present day. Language, values, technology, social structures, political systems, all have transformed beyond recognition. A generation ship launched today, carrying a community shaped by 21st century culture, would undergo similar transformations over 600 years. The society that arrives at Barnard's Star would bear little resemblance to the one that departed. It might not remember why it left. It might not care about the mission. It might have developed beliefs, customs, and priorities that are incompatible with the original objectives. The generation ship solves the distance problem by distributing it across time. But it creates a civilizational problem that may be fundamentally unsolvable. No engineer can design a society that remains stable for 6 centuries. That is a challenge for a completely different kind of science, one that does not yet exist. The second approach is the fast probe. Abandon any notion of sending humans. Instead, send a tiny, lightweight robotic probe at a significant fraction of the speed of light, using beamed energy propulsion. This is the breakthrough starshot concept. The idea, as described by Yuri Milner, Stephen Hawking and Freeman Dyson in 2016, is to build a ground-based laser array capable of producing 100 gigawatts of coherent light. This array would be used to accelerate tiny probes, called star chips, each weighing roughly 4 grams, equipped with a camera, a spectrometer, a communication laser, and a light sail roughly 4 meters in diameter. The laser would fire for approximately 10 minutes, accelerating each probe to roughly 20% of the speed of light. At that speed, the probe would reach Barnard's star in about 30 years. The physics behind laser sail propulsion is elegant. When photons strike a reflective surface, they impart momentum equal to twice their own momentum because the photon is reflected rather than absorbed. The force is tiny per photon, but a 100-gigawatt laser produces an enormous number of photons per second. For a 4-gram probe with a highly reflective sail, the acceleration can be tremendous, hundreds or thousands of Gs, sustained for the few minutes during which the probe remains close enough to the laser for the beam to be effectively focused. The probe is accelerated from rest to 20% of light speed in roughly 10 minutes, experiencing forces that would crush any biological organism but that a solid-state electronic payload can withstand. The numbers are striking. The approach elegantly sidesteps the rocket equation by not carrying any fuel. The energy comes from an external source, the laser array, and only needs to be applied during the brief acceleration phase. The probes are so small that the energy requirements, while enormous by terrestrial standards, are at least conceivable. 100 gigawatts is roughly the total electrical generating capacity of a medium-sized country, but it only needs to be sustained for minutes, not years. But the limitations are equally striking. The probes can only carry a few grams of instruments. At 20% of light speed, they would traverse the Barnard star system in a matter of hours, collecting data during a brief flyby. They would have no ability to slow down, no ability to orbit, no ability to land, and no ability to transmit more than a whisper of data back to Earth across a distance of 6 light-years. The communication challenge alone is formidable. A 4-gram probe with a tiny laser transmitter sending data across 6 light-years would produce a signal so faint that receiving it would require an antenna array on Earth the size of a football stadium, operating at the limits of theoretical sensitivity. And the probes carry no means of course correction beyond the initial few minutes of laser-driven acceleration. Once the laser shuts off, the probe is on its own, coasting through interstellar space for 30 years with no way to adjust its trajectory. Any error in the initial pointing, any deviation from the planned course caused by uneven acceleration, interstellar gas drag, or gravitational perturbations would compound over the decades-long journey. Hitting a target 6 light-years away with a 4-gram projectile launched by a 10-minute laser pulse is an aiming challenge of extraordinary precision. The pointing accuracy required is roughly 10 to the negative 10th radians, which is equivalent to hitting a coin from a distance of roughly 10,000 kilometers. There is also the question of the laser array itself. 100 gigawatts is a staggering amount of power. For comparison, the total electrical generating capacity of the United States is roughly 1,100 gigawatts. The Starshot array would consume roughly 9% of the entire US electrical grid's capacity, focused into a coherent beam. Building such an array would require advances in laser technology, power generation, and optical engineering that are significant but perhaps achievable within a few decades. However, the array would also function as the most powerful directed energy weapon ever created, capable of delivering devastating amounts of energy to any target within its range. The geopolitical implications of building such a device are considerable. International agreements, safety protocols, and oversight mechanisms would need to be established, and the political will to build what is simultaneously a scientific instrument and a weapon of unprecedented power would need to be sustained across decades of development. The probes themselves would also face the interstellar medium at 20% of light speed. At 60,000 kilometers per second, even the sparse gas and dust of interstellar space becomes dangerous. Each hydrogen atom impacted at this speed would carry the kinetic energy of a cosmic ray. The cumulative erosion and heating of the probe's forward surface over 30 years of travel would be significant, potentially degrading the instruments, damaging the sail, or disrupting the communication laser. The probes might arrive at Barnard's star non-functional, their sensors blinded, their communications silent, victims of the same hostile environment that threatens every interstellar traveler. Breakthrough starshot is a brilliant concept. It represents genuine scientific creativity, but it is not interstellar travel in any meaningful sense. It is interstellar photography. It sends a message, not a presence. It takes a picture, not a step. The gap between what starshot can achieve and what would be needed for any form of meaningful exploration, let alone habitation, is orders of magnitude in mass, energy, and capability. A 4-gram probe and a 4,000-kilogram robotic explorer are separated by 6 orders of magnitude in mass, and the energy requirements scale proportionally. Starshot is a beginning, a first whisper across the void. But it is a whisper, not a shout, and certainly not a footstep. The third approach attempts to split the difference between the slow ship and the fast probe. It proposes a moderately fast, unmanned probe with significant scientific capability. This is the domain of designs like Project Daedalus and its successor, Project Icarus. Project Icarus was a study initiated in 2009 by the Tau Zero Foundation and the British Interplanetary Society as an update to Project Daedalus. While Daedalus was designed in the 1970s and was limited by the technology and knowledge of that era, Icarus aimed to incorporate 30 years of advances in physics, engineering, and materials science. The study considered a range of propulsion concepts, including inertial confinement fusion, beam core antimatter, and magnetically confined fusion. It explored the possibility of deceleration at the destination, which Daedalus had not included. The Icarus design targets were ambitious. The probe should reach Barnard's star, or a similar nearby star, within 100 years. It should carry enough scientific payload to conduct a thorough survey of the destination system, and it should be capable of decelerating to orbital velocity, allowing extended study of any planets or other objects found there. These requirements immediately collide with the constraints we have outlined. A 100-year mission to Barnard's star requires an average speed of roughly 6% of the speed of light. Achieving this speed, carrying enough fuel for deceleration, and delivering a meaningful scientific payload requires a spacecraft of enormous mass, likely tens of thousands of metric tons. The Icarus team explored several propulsion options. Inertial confinement fusion, similar to what was proposed for Daedalus, remains the most promising. In this approach, pellets of deuterium-tritium or deuterium-helium-3 fuel are compressed and heated by laser or particle beams until fusion ignition occurs. The resulting plasma is expelled at high velocity through a magnetic nozzle. The exhaust velocity is potentially very high, in the range of 10,000 to 30,000 kilometers per second, which dramatically reduces the mass ratio compared to chemical or nuclear thermal rockets. It is worth pausing to appreciate the engineering complexity of this propulsion system. Inertial confinement fusion has been studied on Earth for decades, most notably at the National Ignition Facility at Lawrence Livermore National Laboratory in California. In December 2022, NIF achieved fusion ignition for the first time, producing more energy from a fusion reaction than the laser energy used to initiate it. This was a landmark achievement, but NIF is a building-sized facility that fires one shot at a time, with weeks of preparation between shots. A Daedalus or Icarus drive would need to fire 250 times per second continuously for years. The gap between a single laboratory fusion shot and a sustained high-rate fusion drive operating in deep space is comparable to the gap between lighting a match and operating a jet engine. The physics is related. The engineering is worlds apart. Moreover, the fusion fuel itself presents challenges. Deuterium is abundant, extractable from seawater at low cost, but helium-3 the preferred fusion partner for many interstellar drive concepts, is extraordinarily rare on Earth. The total estimated terrestrial supply of helium-3 is only about 15,000 metric tons, mostly generated by the decay of tritium in nuclear weapons. The Moon's surface contains larger quantities, implanted by the solar wind over billions of years, with estimates ranging from 100,000 to several million metric tons in the top few meters of lunar soil. But extracting it would require mining operations on a vast scale, processing millions of metric tons of lunar regolith to extract grams of helium-3. Jupiter's atmosphere contains helium-3 in much greater abundance, but harvesting it would require atmospheric mining operations at Jupiter, a planet with a surface gravity 2.5 times Earth's and no solid surface, surrounded by intense radiation belts. Neither option is remotely feasible with current technology. But even with high exhaust velocities, the mass ratio for a mission that includes deceleration is daunting. At an exhaust velocity of 10,000 km per second and a total delta V of roughly 36,000 km per second, accounting for both acceleration and deceleration, the mass ratio is roughly e to the 3.6, or about 37 to 1. This means that for every kilogram of payload and structure that arrives at Barnard's star, the spacecraft must start with 37 kilograms of fuel. A 100 metric ton payload, a modest scientific suite, would require roughly 3,700 metric tons of fuel. A 1,000 metric ton payload, a more capable mission, would require 37,000 metric tons. These numbers are large but not absurd in the abstract. They are in the range of what Project Daedalus envisioned, but translating them into reality reveals the true scale of the challenge. 37,000 metric tons of helium-3, obtained from Jupiter's atmosphere, would require an industrial operation in the outer solar system that dwarfs anything humanity has ever undertaken. It would require space stations orbiting Jupiter, atmospheric scooping vehicles descending into the gas giant's clouds, processing facilities to separate helium-3 from the vastly more abundant helium-4, storage and transport infrastructure to move the fuel to the spacecraft assembly point, and all of this built and operated at a distance of roughly 5 astronomical units from the Sun, where solar power is weak, communication delays are tens of minutes, and the radiation environment is lethal to unshielded humans. The Icarus study did not produce a final design. It produced a range of design options, each with its own set of advantages and challenges, and none that could be built with current technology or within the current century. The study confirmed what Daedalus had suggested 3 decades earlier. An unmanned interstellar probe is theoretically possible within the known laws of physics. But the engineering, economic, and logistical requirements are so far beyond current capabilities that realization is centuries away at minimum. And even centuries of progress may not be enough, because the fundamental constraints, the rocket equation, the energy costs, the reliability requirements, are not engineering problems. They are physics problems. And physics does not become easier with time. There is a variation on the crude approaches that deserves mention. Hibernation, or torpor, has been proposed as a way to bridge the gap between human lifespan and interstellar journey time. If the crew could be placed in a state of suspended animation, their metabolism dramatically slowed or halted, they could survive a journey of centuries or millennia without aging, without consuming resources, and without experiencing the psychological burden of decades in confinement. The biological basis for this idea comes from natural hibernation in mammals such as bears, ground squirrels, and some bat species. During hibernation, these animals reduce their metabolic rate to a fraction of normal, lower their body temperature, and can survive for months without eating. Some species of frogs and turtles can survive being partially frozen, entering a state of cryptobiosis in which biological activity effectively ceases. But human hibernation is far more speculative. Humans are not natural hibernators. Our physiology is not adapted for extended periods of dramatically reduced metabolism. Attempts to induce therapeutic hypothermia in medical settings, such as after cardiac arrest, involve cooling the body by only a few degrees and maintaining the state for hours, not years. The challenges of cooling a human body to temperatures low enough for genuine suspended animation, maintaining cellular integrity during the cooling process, preventing ice crystal formation that would rupture cells, and then safely rewarming the body after decades or centuries of storage are immense. No mammal has ever been revived after more than a few hours of deep hypothermia, and the damage caused by prolonged cold exposure at the cellular level is not well understood. Even if human hibernation could be achieved, it would not solve all the problems of interstellar travel. The spacecraft would still need to function reliably for the entire journey, maintaining life support for the sleeping crew, protecting them from radiation, navigating to the destination, and performing the deceleration maneuver. The crew would be unable to monitor or maintain the spacecraft during transit. Any failure in a critical system, a micrometeorite strike, a cosmic ray hit on a vital computer component, a slow leak in the hull, would be undetected and uncorrected until it was too late. The hibernating crew would be the most vulnerable travelers in history, unconscious, defenseless, and utterly dependent on machines that must function perfectly for centuries. The fourth approach is perhaps the most creative. It proposes not to travel to Barnard's star at all, at least not in the conventional sense. Instead, it proposes to use robotics and artificial intelligence to extend our presence across interstellar distances without sending biological humans. The concept, sometimes called a von Neumann probe after the mathematician John von Neumann, who first described self-replicating machines in the 1940s and 50s, envisions a robotic spacecraft capable of reproducing itself from raw materials found at its destination. A von Neumann probe would travel to a nearby star system, mine asteroids or other bodies for raw materials, build one or more copies of itself, and send those copies to additional star systems. The process would repeat, with each generation of probes spreading further into the galaxy. The mathematical elegance is compelling. If each probe takes 1,000 years to reach a nearby star and 100 years to replicate, the galaxy could be saturated with probes in as little as a few million years. The Milky Way is roughly 100,000 light-years across, and with an average spacing of 5 light-years between probes and a propagation speed of 5% of light speed, the entire galaxy could be explored in roughly 10 million years. This is a long time by human standards, but a short time by galactic standards. The Milky Way is roughly 13 billion years old. 10 million years is less than 1/10 of 1% of the galaxy's age. But here's the problem. We do not know how to build a self-replicating machine. The concept is well defined mathematically, but the engineering is staggeringly complex. A self-replicating probe would need to mine raw materials from an asteroid or planet, refine those materials into usable metals, semiconductors and composites, fabricate every component of itself, from structural members to microchips to sensors to power systems, and assemble those components into a functioning replica. This implies the equivalent of an entire industrial civilization contained within a single spacecraft. Mining, smelting, machining, lithography, assembly, testing, software installation, all performed autonomously, in an alien environment, from unknown raw materials, with no external support. Current robotic systems are capable of performing specific, well-defined tasks in controlled environments. They can weld, paint, cut, and assemble components in a factory setting where every variable is known. They can navigate terrain on Mars and drill into rocks with pre-programmed sequences. But they cannot do all of these things simultaneously in an unknown environment with no human oversight, and they certainly cannot manufacture copies of themselves from raw materials. The gap between current robotics and a self-replicating interstellar probe is not a gap that can be bridged by incremental improvement. It requires a qualitative leap in artificial intelligence, materials science, manufacturing technology, and robotic dexterity that may be decades or centuries away, if it is achievable at all. Consider what self-replication actually entails. The probe arrives at a star system and identifies a suitable asteroid. It must analyze the asteroid's composition, determine which minerals and elements are present, and develop a mining plan. It must land on or attach to the asteroid, which may be tumbling, irregularly shaped, and composed of unknown materials. It must mine the raw ore, crush it, sort it, and refine it into usable metals, silicon, carbon, and other elements. It must then fabricate every component of a new probe, from structural beams to solar panels to microprocessors to sensors to communication systems to propulsion units. The fabrication of microprocessors alone currently requires facilities that cost billions of dollars, occupy entire buildings, and operate in clean rooms with fewer than 100 particles per cubic meter. Replicating this capability in a spacecraft the size of a school bus, operating autonomously on an asteroid billions of kilometers from Earth, is not an engineering challenge. It is a different kind of problem, one for which we do not currently have even a theoretical framework. And there is a philosophical dimension to the von Neumann concept that is worth considering. If the probes are truly self-replicating, they will inevitably accumulate copying errors over successive generations, just as biological organisms accumulate mutations. Without some form of error correction or natural selection, the probes would drift from their original design over time, potentially becoming less functional or evolving in unintended directions. A sufficiently advanced self-replicating probe might, over millions of years and billions of generations, become something quite different from what was originally launched. The galaxy might be seeded not with our explorers, but with our descendants, mechanical offspring that bear little resemblance to their creators and pursue goals we never imagined. The ethical implications of releasing self-replicating machines into the galaxy, even with the best of intentions, are profound and largely unexplored. And even if von Neumann probes could be built, they would not solve the fundamental problem for human beings. They would extend our robotic presence, not our physical presence. They could explore, observe, and report back, but the data would take years to reach us, and we could not interact with the destination in real time. Von Neumann probes are, in a sense, an admission that humans cannot go to the stars. They are a substitute for human exploration, not an enabler of it. There is also a darker implication of the von Neumann probe concept. If self-replicating probes are possible, and if they could saturate the galaxy in a few million years, then the Fermi paradox becomes even more acute. If any civilization in the Milky Way's 13 billion-year history had ever built von Neumann probes, those probes should every star system in the galaxy by now, including ours. We should see their descendants orbiting our sun, mining our asteroids, studying our planet. We do not. The absence of von Neumann probes in our solar system is either evidence that no civilization has ever built them, which suggests that the engineering challenges are even harder than we think, or evidence that civilizations that build self-replicating machines tend to encounter problems we have not anticipated. Perhaps the probes malfunction. Perhaps they evolve in unintended ways. Perhaps they consume their creators. The silence of the galaxy is not reassuring. The fifth approach is the most speculative and the most radical. It proposes to abandon the physical body entirely and send only information, transmitting the data necessary to reconstruct a human mind or a simulation of one to a receiver at the destination. This concept is sometimes called digital interstellar travel, uploaded consciousness, or substrate-independent minds. The concept envisions a future in which the human mind can be scanned, digitized, and transmitted as a data stream at the speed of light. The data would be sent via laser or radio to a receiving station at Barnard's star, where it would be used to instantiate a digital consciousness in a robotic body, a synthetic biological body, or a virtual environment. The transmitted mind would experience continuity of consciousness, waking up at the destination as though it had traveled there, even though the original biological body remains on Earth or has long since died. The journey takes 6 years, the time for light to cross the distance, and the traveler experiences no subjective passage of time during transit. This approach neatly avoids many of the constraints we have discussed. There is no mass to accelerate. There is no fuel to carry. There is no life support to maintain. There is no radiation to shield against. There is no waste heat to manage. The data stream travels at the speed of light, the fastest possible speed, reaching Barnard's star in 6 years. The energy requirements for transmission are modest, far less than what is needed to accelerate even a gram of physical matter to a significant fraction of light speed. But the limitations are profound and may be permanent. First, We do not know how to scan and digitize a human mind, and it is not clear that we ever will. The human brain contains roughly 86 billion neurons, connected by roughly 100 trillion synapses, each with its own strength, timing, and plasticity. The complete connectome of a human brain has never been mapped. The largest connectome mapped to date is that of the fruit fly, which has roughly 139,000 neurons, a tiny fraction of the human brain's complexity. The resolution required for a faithful scan of a human brain may be at the molecular or even quantum level, requiring imaging technologies that do not exist and may not be physically possible without destroying the brain in the process. Whether consciousness can even be reduced to data, whether a digital simulation of a brain would be conscious, whether the uploaded mind would be the same person or merely a copy, these are not just technological questions. They are philosophical ones that have been debated for centuries under various names: the mind-body problem, the hard problem of consciousness, the question of personal identity, and they may have no definitive answer. A digital copy of your mind might behave exactly like you, respond exactly like you, claim to be you, and still not be you in any meaningful sense. The question of whether the lights are on inside the simulation, whether there is subjective experience rather than mere information processing, may be unanswerable. Second, there must be a receiver at the destination. Someone or something must build the infrastructure at Barnard's star to receive the data stream, process it, and reconstruct the mind in a physical or virtual substrate. This infrastructure does not exist, and building it requires either sending physical hardware to the destination first, which brings us back to all the problems of physical interstellar travel, or relying on von Neumann probes to construct the receiving station autonomously. Each approach depends on solving problems we have already identified as unsolvable with current technology. Digital interstellar travel is the most creative and the most far-future of the approaches we have considered. It avoids the mass problem, the fuel problem, the biological problem, and the time problem. But it creates entirely new problems that are equally daunting, and it depends on philosophical assumptions about the nature of consciousness that may never be resolved. It is the ultimate expression of human ingenuity applied to an intractable problem, and it may be the ultimate illustration of how intractable the problem truly is. So where does this leave us? 5 approaches, spanning the full range from conservative engineering to radical speculation. The slow ship can make the journey, but it requires a civilizational commitment spanning centuries, with no guarantee of success. The fast probe can send a whisper across the void, but it cannot send a presence. The fast unmanned probe can deliver scientific capability, but it requires an industrial base we do not have, and fuel we cannot obtain. The von Neumann probe can explore the galaxy, but it cannot send us, and digital transmission can send our minds, but only if we can solve problems that may be unsolvable. Every approach confronts the same underlying reality. Barnard's star is 6 light-years away. 6 light-years is roughly 57 trillion kilometers. The energy required to cross that distance at any meaningful speed is enormous. The time required at any achievable speed is immense. And the engineering challenges at any timescale are beyond anything we have ever attempted. The universe is not hostile to interstellar travel in the way that it is hostile to perpetual motion or faster-than-light communication. It does not forbid it outright with a clean, simple prohibition. Instead, it does something more subtle and more effective. It taxes it. It imposes costs at every step: energy costs, time costs, mass costs, reliability costs, biological costs, sociological costs. Each cost is large. Their combination is overwhelming. It is as though the universe has placed not a single barrier in the path to the stars, but a series of tolls, each one demanding payment in a different currency. Each one set at a level that strains our resources to the breaking point. And the tolls must all be paid simultaneously, on the same journey, by the same travelers. The result is that interstellar travel, while not physically impossible, is practically impossible in a way that is qualitatively different from any challenge we have previously faced. Previous challenges, crossing the Atlantic, reaching the moon, splitting the atom, were hard but achievable with concentrated effort over years or decades. Reaching Barnard's star is hard in a different way. It requires concentrated effort over centuries or millennia, at resource levels that dwarf anything a single nation or generation can provide, against physical constraints that do not soften with time or technology. It is not the next step in a progression. It is a wall at the end of a road. The Soviet astronomer Nikolai Kardashev proposed a classification scheme in 1964 that ranks civilizations by their energy consumption. A Type 1 civilization harnesses all the energy available on its home planet, roughly 10 to the 16th to 10 to the 17th watts. A Type 2 civilization harnesses all the energy of its star, roughly 10 to the 26th watts. A Type 3 civilization harnesses all the energy of its galaxy, roughly 10 to the 36th watts. Humanity is currently a Type 0.73 civilization, by most estimates consuming roughly 10 to the 13th watts. The energy required for a meaningful interstellar mission, not a flyby but an actual expedition to Barnard's star with scientific capability and the ability to stop, is roughly in the range of 10 to the 20 to 10 to the 22 joules, depending on the mission profile. Delivering this energy over a multi-year acceleration phase requires sustained power in the range of 10 to the 12 to 10 to the 14 watts, comparable to the total power output of human civilization. An interstellar-capable civilization, one that could routinely send probes or ships to nearby stars, would need to be at least a high-type Wadton civilization, commanding planetary-scale energy resources. We are not there. We may not be there for centuries. And even when we arrive at that level of energy mastery, the physics of the journey will not have changed. The rocket equation will still apply. The speed of light will still be the limit. The interstellar medium will still be hostile. The only thing that changes is the scale of resources we can bring to bear against a problem that may simply be too large. And this is where the answer becomes deeply unsettling. Because if Barnard's star, 6 light-years away, the second closest stellar system to our Sun, is beyond our reach, then what does that say about every other star in the galaxy? What does that say about the 100 billion to 400 billion stars in the Milky Way, or the 2 trillion galaxies in the observable universe, each with its own hundreds of billions of stars? If we cannot reach our nearest neighbour, we cannot reach any of them. The stars are not destinations. They are scenery, beautiful, magnificent, awe-inspiring scenery, but scenery nonetheless, visible but untouchable, close enough to study, far enough to never visit, ours to contemplate but never to possess. This is a difficult truth to accept, because it contradicts one of the deepest narratives of human culture. We tell ourselves stories about exploration, about frontiers, about pushing beyond the known into the unknown. We celebrate Columbus, Magellan, Armstrong. We assume that the cosmos is the next frontier, that the stars are waiting for us, that we will go there someday. But the evidence suggests otherwise. The stars are waiting, perhaps, but they are waiting at a distance so great, across a void so hostile, behind barriers so fundamental that waiting is all they will ever do, and all we will ever do is watch. There is something profoundly strange about being a species that can see billions of light-years into the cosmos, but cannot physically cross 6. We can photograph galaxies that are 13 billion light-years away. We can measure the temperature of the universe when it was 380,000 years old. We can detect gravitational waves from colliding black holes a billion light-years distant. Our eyes, augmented by our instruments, can reach across the entirety of the observable cosmos. But our hands cannot reach the nearest star. The asymmetry between our ability to observe and our ability to reach is perhaps the most striking feature of our cosmic situation. We are the most far-sighted species in the known universe, trapped on a single rock, looking out at everything we can never touch. The deeper truth about Barnard's star is not about Barnard's star at all. It is about the nature of the universe we inhabit and the place we occupy within it. The inability to reach even the nearest stars is not a temporary embarrassment that future technology will resolve. It is a structural feature of reality, a consequence of the same physical laws that allow matter to exist and stars to shine, and its implications reach far beyond the question of interstellar travel. Let us begin with the most unsettling implication. If we cannot reach Barnard's star, and if the same constraints apply to every other civilization in the galaxy, then the Fermi paradox takes on a new and darker significance. The Fermi paradox, named after the Italian-American physicist Enrico Fermi, who posed the question during a lunch conversation at Los Alamos National Laboratory in 1950, asks a deceptively simple question. If the universe is vast and old, and if the conditions for life are common, then where is everybody? The Milky Way contains between 100 billion and 400 billion stars. It is roughly 13 billion years old. Even if intelligent, technological civilizations are rare, arising around only one star in a million, there should still be hundreds of thousands of them in our galaxy alone. And even if interstellar travel is slow, requiring thousands of years between stars, a single civilization could colonize the entire galaxy in a few million years, a blink of an eye in galactic time. So, where are the colonizers? Where are the probes? Where are the signals? The galaxy should be teeming with evidence of technological civilizations. It appears to be silent. Many solutions have been proposed. Perhaps intelligent life is rarer than we think. Perhaps the emergence of multicellular life, or photosynthesis, or eukaryotic cells, or any of a dozen critical evolutionary transitions is so improbable that it happens only once in a billion galaxies. This is the rare Earth hypothesis, articulated by geologist Peter Ward and Donald Brownlee in their 2000 book of the same name. Perhaps civilizations tend to destroy themselves before achieving interstellar capability, succumbing to nuclear war, environmental collapse, pandemic, or some other existential catastrophe. This is the great filter hypothesis, which suggests that somewhere along the path from simple chemistry to interstellar civilization, there is a step so unlikely or so dangerous that almost nobody makes it through. Perhaps advanced civilizations are out there, but deliberately hiding, observing us from a distance without revealing themselves, a scenario sometimes called the zoo hypothesis or the dark forest hypothesis. Perhaps the universe is simply too young, and we are among the first civilizations to emerge, still waiting for the galaxy to fill. Or perhaps the explanation is simpler, more structural, and more permanent than any of these. Perhaps the distances between stars are themselves the answer. Perhaps the laws of physics, the speed of light, the energy costs of propulsion, the hostility of the interstellar medium constitute a barrier so fundamental that no civilization, no matter how advanced, can meaningfully cross it. Not because they are insufficiently clever, but because the universe does not permit it. This last possibility, which we might call the Great Barrier Hypothesis or the cosmic quarantine, is the one most directly supported by the analysis we have conducted tonight. The constraints on interstellar travel are not peculiar to human technology, they are universal. The speed of light is the same everywhere. The rocket equation applies to every chemical and nuclear propulsion system, regardless of who builds it. The interstellar medium is hostile to every spacecraft, regardless of its origin. The energy costs are dictated by the laws of thermodynamics, which do not vary from one civilization to another. If we cannot reach Barnard's star, it may be because no civilization can, at least not at a cost that makes sense. Let that sink in. The stars may not be unreachable because we are insufficiently advanced. They may be unreachable because the universe is designed, if we can use that word loosely, to keep its inhabitants apart. The distances between stars, the hostility of interstellar space, the speed of light, the rocket equation, the energy costs, all of these may function as a natural quarantine, isolating every civilization on its home world or within its home stellar system, preventing contact, preventing colonization, preventing the galaxy-spanning empires of science fiction from ever forming. This is not science fiction. This is the straightforward extrapolation of known physics to the problem of interstellar travel. The laws of physics do not prohibit interstellar travel outright, but they tax it so heavily that only the most modest missions, tiny flyby probes carrying grams of instruments, are even theoretically feasible within the next century. Meaningful interstellar travel, the kind that sends people or sophisticated robots to other star systems with the ability to stop, explore, and report back, may require civilizational resources that no society can sustain long enough to deploy. And if this is true, then every civilization in the galaxy is alone. Not because life is rare. Perhaps life is common. Perhaps intelligence is common. Perhaps the galaxy is filled with millions of civilizations. each one looking up at its own night sky, each one wondering whether anyone else is out there, each one calculating the energy costs and the time scales and the mass ratios, and each one arriving at the same dispiriting conclusion. The distance is too great, the energy is too expensive, the time is too long, the stars are beautiful, and they are out of reach. Let that sink in. The loneliness we feel when we look at the stars may not be the loneliness of a rare species in an empty universe. It may be the loneliness of one of countless species in a universe that is structured, at the most fundamental level, to keep them apart. The cosmic quarantine is not imposed by any intelligence or any malice. It is imposed by physics, by the speed of light, by the rocket equation, by the thermodynamics of propulsion, by the simple, brutal fact that crossing 6 light-years requires more energy, more time, and more reliability than any civilization we can imagine is likely to command. The quarantine is not a conspiracy. It is not a policy. It is a consequence of living in a universe where the speed limit is 300,000 kilometers per second, where the energy content of matter is governed by E equals mc squared, where entropy always increases, and where the nearest star is 25 trillion miles away. Some have called this the Great Silence, the absence of detected signals from other civilizations, the absence of probes in our solar system, the absence of any evidence that anyone else has ever visited this corner of the galaxy. The Great Silence may not be a mystery at all. It may be the natural, expected, inevitable consequence of the physics that governs every star system, every civilization, every intelligent species that has ever looked up at its own sky and wondered whether the lights above were places it could go. The silence is not eerie. It is structural. It is built into the fabric of the cosmos, as intrinsic as gravity, as fundamental as light, and it applies equally to us and to them, whoever they are, wherever they are, however advanced they have become. The stars are silent because the ocean between them is too wide, and the ships too slow, and the fuel too heavy, and the journey too long. And so the silence endures, and will endure, and has always endured. There is a concept in ecology called island biogeography, developed by the biologists Robert MacArthur and E.O. Wilson in the 1960s. It describes how species diversity on islands is determined by the balance between immigration and extinction, which in turn is determined by the island's size and its distance from the mainland. Distant islands have fewer species because fewer organisms can cross the water to reach them. The ocean acts as a barrier, filtering out all but the most mobile and adaptable species. The further the island from the mainland, the more impoverished its ecosystem. The analogy to stellar systems is striking, and it goes deeper than a surface resemblance. Each star system is an island. The interstellar void is the ocean. The width of the ocean, measured in light years, determines how isolated each island is. And the physics of interstellar travel, the energy costs, the timescales, the hostility of the medium, functions as a filter, one so severe that nothing, or almost nothing, can cross it. Each stellar system is a biological island, possibly hosting its own ecosystem, possibly hosting intelligence, but isolated from every other island by an ocean of vacuum that is, for practical purposes, uncrossable. In island biogeography, the size of the barrier determines the degree of isolation. Small gaps between islands allow frequent exchange. Large gaps allow almost none. The interstellar ocean is not merely large. It is, in practical terms, infinite in width relative to the capabilities of any known swimmer. The nearest island, Proxima Centauri, is 4.24 light-years away. The next, Barnard's star, is 6. These are not large gaps by cosmic standards, but by the standards of any technology that obeys the known laws of physics. They are effectively uncrossable barriers. MacArthur and Wilson showed that isolated islands tend to develop unique ecosystems, driven by random variation and local adaptation rather than by exchange with a wider community. If this principle applies to stellar systems, then each star system with life may harbor its own unique biosphere, its own unique evolutionary history, its own unique forms. And if intelligence arises in some of those biospheres, each intelligent species may develop its own unique culture, its own unique technology, its own unique understanding of the cosmos, all in isolation, all without contact, all without the exchange of ideas, genes, or resources that has driven so much of evolution and cultural development on Earth. The galaxy may be a library of civilizations, each one a book written in a language no one else can read, each one stored on a shelf that no one else can reach. If this picture is correct, then the galaxy is not a community. It is an archipelago of loneliness, each island separated from its neighbors by gaps that no ship can bridge, no signal can meaningfully traverse in real time, and no civilization can afford to cross. The galaxy may be filled with life, but that life is confined, trapped, marooned on individual worlds or in individual star systems, looking out at the lights of other islands across an impassable sea, each one wondering whether anyone else exists, each one unable to confirm it, each one alone with its questions and its calculations, arriving at the same answers and the same silence. The galaxy hums with potential, and the potential goes unrealized, not because of any failure of will or intellect, but because the physics forbids it. Now let us consider what this means for the long-term future of humanity. If we accept that interstellar travel is, at best, extraordinarily difficult and at worst, fundamentally impossible for biological civilizations, then our future is bound to our home star, the Sun, our solar system. Perhaps, with enormous effort over centuries, we could expand to the other planets and moons of our solar system. Mars, the moons of Jupiter and Saturn, the asteroids. This is challenging but conceivable. The distances are manageable. The energy costs are high but not insurmountable. The timescales are years, not millennia. But the solar system is finite. It contains enormous resources by terrestrial standards. The asteroid belt alone contains enough metal to supply human industry for millions of years. The outer planets contain vast quantities of hydrogen, helium, and other gases. The comets of the Oort cloud contain trillions of tons of water ice. A civilization that fully exploited the resources of the solar system would be unimaginably wealthy by our current standards, commanding energy flows measured in petawatts and material resources measured in quadrillions of metric tons. But even this abundance has limits. The Sun has roughly 5 billion years of hydrogen fuel remaining. After that, it will exhaust its core hydrogen, swell into a red giant star, roughly 200 times its current diameter, engulfing the orbits of Mercury, Venus, and possibly Earth, and then shed its outer layers to form a planetary nebula, leaving behind a white dwarf roughly the size of the Earth, but with the mass of half the Sun. This white dwarf will slowly cool over trillions of years, radiating less and less energy, eventually fading to a cold, dark cinder called a black dwarf, a theoretical endpoint that the universe is not yet old enough for any star to have reached. If humanity, or whatever we become over the next 5 billion years, is still confined to the solar system, when the Sun enters its red giant phase, we will need to adapt or perish. Moving outward to the Kuiper belt, or the Oort cloud, might buy additional time, harvesting energy from the white dwarf's residual heat or from fusion of stockpiled hydrogen. But eventually the energy runs out. The white dwarf cools. The fusion fuel is consumed, and the solar system, once a vibrant oasis of energy and matter, becomes a frozen, dark graveyard. If we cannot escape to another star, we get one stellar lifetime, roughly 10 billion years from the Sun's ignition to the white dwarf's final cooling. That is our window. It is generous by human standards, enormously so, far longer than our species has existed or is likely to exist in its current form. But it is finite, and if the stars are truly unreachable, then humanity's entire future, from this moment to the last moment, is contained within this one stellar system. Every human triumph and tragedy, every discovery and loss, every civilization that rises and falls, will happen here, around this one star, in this one corner of the galaxy. The rest of the cosmos will remain forever beyond our reach, visible but untouchable, known but unexplored, a vast and silent cathedral in which we are permitted to listen, but never to speak. There are those who argue that technology will eventually solve the interstellar problem, that fusion drives, antimatter engines, warp drives, or some as yet undiscovered physics will open the stars to us. Perhaps they are right. The history of technology is filled with examples of things that were once considered impossible, but were later achieved. Heavier-than-air flight was considered impossible until the Wright brothers flew at Kitty Hawk in 1903. Nuclear energy was considered impossible until Enrico Fermi achieved the first sustained nuclear chain reaction in 1942. Landing on the moon was considered impossible until Apollo 11 touched down in the Sea of Tranquility in 1969. But there is a crucial difference between these achievements and interstellar travel. And it is a difference that most optimistic projections fail to acknowledge. Each of these breakthroughs operated within the known laws of physics. The Wright brothers did not violate aerodynamics. They exploited it. The principles of lift, drag, and thrust were well understood before their flight. What they achieved was an engineering solution to a physics problem that had a solution. Fermi did not violate nuclear physics. He harnessed the chain reaction that physics predicted and that nature performs in every star. The Apollo program did not violate orbital mechanics. It applied them with extraordinary precision, using trajectories that Newton's equations had described 2 centuries earlier. Interstellar travel, as we have seen, does not merely face engineering challenges that can be solved within the existing physics. It faces challenges imposed by the fundamental laws of physics themselves. The speed of light is not a speed limit that can be exceeded with a better engine. It is a structural feature of space-time, woven into the geometry of the universe at the deepest level. The rocket equation is not a limitation of chemical rockets. It applies to every reaction drive, nuclear, fusion, antimatter, regardless of technology. The energy mass equivalence, E equals mc squared, sets the absolute maximum energy that can be extracted from a given mass of fuel, and no technology can extract more. The second law of thermodynamics ensures that every energy conversion produces waste heat, and no technology can eliminate that waste. These are not engineering problems that better technology can solve. They are physical laws that better technology must obey, and obeying them, while crossing 6 light-years, requires resources and timescales that may simply be beyond the reach of any civilization bound by those same laws. The laws of physics are not challenges to be overcome. They are the rules of the game, and the rules say that interstellar travel is extraordinarily, perhaps prohibitively, expensive in every currency that matters. Energy, time, mass, reliability, biological endurance. The bill must be paid in all of them simultaneously on the same trip by the same travelers. This does not mean that all hope is lost. It means that the kind of interstellar travel depicted in science fiction, routine travel between star systems, with people stepping off spacecraft onto alien worlds as casually as stepping off an airplane, is almost certainly never going to happen. The reality of interstellar travel, if it happens at all, will be agonizingly slow, staggeringly expensive, and limited to either tiny robotic probes or vast generation ships that are more accurately described as relocating civilizations than traveling vehicles. The drama will not be in the journey. The drama will be in the decision to go, knowing that those who leave will never return, and those who stay will never see them again. There is a passage in the scientific literature that captures this poignantly. In a 2008 paper on the feasibility of interstellar travel, physicist and science fiction author Jeffrey Landis wrote that interstellar travel would not be an extension of existing space travel, but a fundamentally different enterprise, more akin to the founding of a new civilization than to any journey that has come before. The travelers would not be explorers. They would be emigrants. They would leave everything behind, every person they had ever known behind, and step into a void that would consume decades or centuries of their descendants' lives before anything resembling a destination appeared on the horizon. This is not exploration as we understand it. It is exile. It is a permanent, irrevocable departure from everything known, with no possibility of return, no possibility of rescue, and no certainty that the destination holds anything worth reaching. Consider what this means for the human species. We are a species defined by our restlessness, by our refusal to accept limits, by our compulsion to cross every horizon. This drive has taken us from the African savanna to every continent, from the surface of the Earth to the surface of the Moon. It is arguably the defining characteristic of Homo sapiens. We explore, we reach, we go. And now, for the first time in our history, we are confronting a limit that may be permanent. A frontier that does not yield to persistence, ingenuity, or courage. a barrier that is not a challenge to be overcome, but a fact to be accepted. The stars are there. We can see them. We can study them. We can catalogue their planets and analyse their compositions and speculate about what might live on their worlds. But we cannot go there, not because we have not tried hard enough, not because we have not been clever enough, but because the universe charges a price for the journey that may be higher than any civilization can pay. This is a new experience for our species. We have never before encountered a limit that we could not eventually transcend, and it forces a reckoning. If we cannot go to the stars, then what is the point of looking at them? If the frontier is closed, then what becomes of the frontier impulse? These questions have no easy answers, but they are the questions that the physics demands we face, and even exile requires a destination worth reaching. Barnard's star, as we have discussed, is a dim red dwarf with uncertain planetary companions. It may have no habitable worlds. It may have no worlds at all. Sending a generation ship to a star that might have nothing worth stopping for is a risk of civilizational proportions. You do not launch a 10,000-year mission to a destination that might be barren. You need certainty, or something close to it. And from 6 light-years away, certainty is exactly what we do not have. The James Webb Space Telescope and its successors may eventually be able to characterize the atmospheres of exoplanets around nearby stars, detecting biosignatures like oxygen, methane, and water vapor that might indicate the presence of life. Future missions, such as the proposed Habitable Worlds Observatory, could directly image Earth-sized planets around Sun-like stars and analyze their atmospheric spectra with sufficient precision to detect signs of biological activity. If a habitable, or better yet an inhabited, world were found orbiting Barnard's star or another nearby star, the calculus might change. A confirmed living world 6 light-years away would be the greatest discovery in human history, the most profound revelation since Copernicus displaced the Earth from the center of the cosmos. It would transform the interstellar travel question from an abstract engineering challenge into a concrete existential imperative. But even then, the physics would remain the same. The journey would still require the same energy, the same time, the same engineering miracles. Motivation does not change the rocket equation. Desire does not reduce the speed of light. The discovery of a living world at Barnard's star would make us want to go more desperately than ever. And it would not make going one bit easier. That is perhaps the cruelest irony of our cosmic situation. The more we discover about the universe around us, the more we learn about the worlds that orbit other stars, the more tantalizing the destinations become, the more acute the agony of our confinement grows. Knowledge amplifies desire. Distance frustrates it. And the gap between what we know and what we can reach only widens with every advance in astronomy. We are temporary patterns in matter and energy, briefly complex enough to understand our own predicament. We live on a small world, orbiting a single star, in a galaxy that contains hundreds of billions of other stars, most of them with planets, many of them possibly with life. And the gaps between those stars, the silent, empty, radiation-filled light-years of nothing, are wider than our technology can cross, deeper than our lifetimes can span, and more hostile than our bodies can endure. This is not a challenge to be overcome. It is a condition to be understood, a boundary to be accepted, a truth to be held. The real reason we will never reach Barnard's star is not that we lack the will. It is not that we lack the intelligence. It is not that we lack the ambition or the courage or the curiosity. The real reason is that the universe charges a price for interstellar travel, and the price is higher than any civilization built from atoms, powered by stars, and limited by the speed of light is likely to pay. The currency is energy, time, and mass. The exchange rate is set by the laws of physics, and the bill for even the shortest possible interstellar journey to the dimmest possible nearby star is staggering beyond all human experience. But there is something else buried in this truth, something that is not entirely bleak. The same physics that imprisons us also reveals the universe to us. We cannot reach Barnard's star, but we can see it. We cannot visit distant galaxies, but we can photograph them, analyze their light, measure their distances, and reconstruct their histories. We are trapped, yes, But we are trapped in a glass house, not a dungeon. The walls are transparent, the view is magnificent, and the view extends in every direction to the edge of the observable universe, 46.5 billion light-years away. No other species on Earth has ever been aware of the stars as objects, as other suns, as potential destinations. No other species has ever measured the distance to another star, or calculated the energy required to reach it, or felt the ache of knowing that the distance cannot be crossed. This awareness, this cosmic consciousness, is unique to us, as far as we know, and it carries with it a peculiar kind of nobility. We are the universe's way of knowing its own structure, even when that structure includes barriers that cannot be breached. We are the cosmos examining its own architecture, even when that architecture includes walls. Perhaps the real achievement is not reaching the stars. Perhaps the real achievement is understanding why we cannot. Every equation we write, every observation we make, every probe we send into the void adds to a body of knowledge that represents the universe's most elaborate act of self-description. We may never set foot on a world orbiting Barnard's star, but we have already reached it, in a sense, with our understanding. We know its mass, its temperature, its age, its velocity, its composition. We know the distance to within a fraction of a percent. We know the challenges of reaching it with an intimacy that comes from decades of careful calculation. We have mapped the obstacle course, even if we cannot run it. And there is a final thought that deserves voice. The universe that contains us also contains Barnard's star. The atoms in our bodies were forged in the cores of ancient stars, distributed by supernova explosions, gathered by gravity into new stars and planets, assembled by chemistry into molecules, and by biology into cells, and by evolution into minds. The iron in our blood was made in a star that exploded before our sun was born. The calcium in our bones was synthesized in a stellar furnace billions of years ago. We are, in a very literal sense, made of the same stuff as Barnard's star. We are stardust contemplating stardust. And while our bodies cannot cross the 6 light-years that separate us from that dim red point of light, our substance is already there. It always was. We are not separate from the stars. We are the stars, rearranged into a shape that asks questions. And the questions themselves are a form of reaching, even if the hands that ask them can never touch what they reach for. What does it mean to live on a world orbiting a star that you can never leave? What does it mean to belong to a species that can see the cosmos in its entirety, but can never touch more than a tiny fraction of it? What does it mean to be aware of your own confinement, to understand the physics that imposes it, and to know that it will not change? These questions matter. They matter not because they have answers, but because the act of asking them is itself a measure of what we are. No rock asks why it cannot fly. No star wonders why it cannot cross the galaxy. Only beings like us, beings complex enough to understand their own situation, experience the vertigo of cosmic limitation. The awareness of the barrier is uniquely human, and how we respond to that awareness says something profound about our character as a species. One response is denial. We tell ourselves that technology will find a way, that future generations will solve the problems we cannot, that the same spirit that put boots on the moon will someday put boots on a world orbiting Barnard's star. This response is understandable. It is deeply rooted in our cultural narrative of progress, in our belief that every problem has a solution, in our refusal to accept limits. But it is not supported by the physics. The constraints on interstellar travel are not engineering problems waiting for a clever solution. They are physical laws, as immovable as gravity, as permanent as the speed of light. Denying them is comforting. It is also dishonest. A second response is despair. If the stars are unreachable, then what is the point? Why study the cosmos if we can never explore it? Why build telescopes if we can never visit the worlds they reveal? Why dream of other stars if the dreams can never be fulfilled? This response, too, is understandable. It is the natural reaction of a species that has always equated knowledge with power, understanding with control, seeing with reaching. If we cannot reach what we see, then seeing feels like torment. The sky becomes a ceiling instead of a frontier. The stars become a reminder of limitation instead of a promise of possibility. But there is a third response, and it is the one that seems most appropriate to our actual situation, the one that honors both the magnificence of what we can see and the reality of what we cannot touch. It is the response of wonder held in tension with acceptance. We can be awed by the universe without needing to possess it. We can study the stars without needing to visit them. We can find meaning in the act of understanding, even when understanding does not lead to action. We can admire the craftsmanship of a cathedral without needing to own it. We can love a landscape without needing to build on it. We can know the cosmos without needing to conquer it. The value of knowledge is not solely instrumental. Knowing the distance to Barnard's star, knowing the temperature of the cosmic microwave background, knowing the age of the universe, knowing the mass of the electron, these things have value in themselves, independent of any practical application. They are the universe knowing itself through us, and that knowing is, in a deep sense, what we are for. Not what we were designed for, because the universe has no designer in any empirical sense, but what we do, what we are, what our existence amounts to. The philosopher Thomas Nagel wrote about the absurdity of human life, the contrast between the seriousness with which we take our lives and the cosmic insignificance of everything we do. If the universe is indifferent to our existence, if our achievements will be forgotten and our civilizations will crumble and our species will eventually go extinct, then what justifies the effort? Nagel's answer was characteristically honest. Nothing justifies it. But the absurdity does not require resolution. We can live with the tension. We can take our lives seriously, even while acknowledging that the cosmos does not share our seriousness. The same principle applies to our relationship with the stars. We can care about the cosmos, study it, marvel at it, and be moved by it, even while accepting that we will never reach most of it. The caring does not require contact. The wonder does not require possession. Consider what we have achieved from our confined position. From the surface of one planet, orbiting one star, in one galaxy, we have mapped the structure of the observable universe to a distance of 46.5 billion light-years. We have detected the afterglow of the Big Bang and used it to determine the age, composition, and geometry of the cosmos with extraordinary precision. We have discovered that the universe is accelerating in its expansion, driven by a mysterious force we call dark energy that makes up 68% of the total energy budget of the cosmos. We have detected gravitational waves from colliding black holes and neutron stars, opening an entirely new window on the universe. We have found more than 5,000 exoplanets and begun to characterize their atmospheres, looking for signs of water, oxygen, and life. We have traced the history of the universe from the first fraction of a second after the Big Bang to the present day, reconstructing a narrative that spans 13.8 billion years. All of this from one planet. All of this without leaving our solar system. All of this with instruments made of the same elements that were forged in the cores of dead stars billions of years ago. If this is confinement, it is the most productive confinement in the history of the cosmos. We are prisoners who have mapped the prison from the inside, deduced its architecture, understood its laws, predicted its future, and reconstructed its past. We are captives who understand their cage better than any free creature has ever understood freedom. There is dignity in that. There is even a kind of triumph. The bars of our cage are made of light years, but our understanding extends far beyond the bars. There is a parable from the ancient world about a man in a cave who can see only shadows on the wall, cast by objects he cannot observe directly. He studies the shadows with care, deduces the shapes of the objects that cast them, and constructs an extraordinarily accurate picture of a reality he can never directly experience. We are that man. The stars are the objects, the photons are the shadows, and our understanding, built from those photonic shadows across billions of years, is one of the great achievements of matter organized into mind. The night sky is not diminished by our inability to cross it. The stars are not less beautiful for being unreachable. The galaxies are not less magnificent for being unvisitable. If anything, their distance and their inaccessibility make them more precious. They are gifts of light arriving after journeys of years and decades and centuries, carrying information about places we will never go, times we will never witness, processes we will never see firsthand. Each photon that reaches our instruments is a messenger from an unreachable world, and the message it carries is the only contact we will ever have. That is not nothing, that is everything. The Voyager 1 spacecraft, launched in 1977, carries a golden record containing sounds and images from Earth, placed there in the slim hope that some other intelligence might someday find it. The record includes greetings in 55 languages, music from Bach to Chuck Berry, sounds of wind and waves and laughter. It is a message in a bottle, cast into an ocean so vast that the probability of anyone finding it is essentially zero. The record will outlast every structure on Earth. It will outlast the pyramids, the continents, the species that made it. In 5 billion years, when the sun expands to swallow our world, the golden record will still be drifting through interstellar space, unharmed, unheard, carrying its cargo of sounds and images from a world that no longer exists. Voyager will drift through interstellar space for billions of years, its instruments long dead, its golden record slowly degrading, its message unheard and unread, and yet we sent it. We carved our names on a pebble and threw it into the void, not because we expected an answer, but because the act of reaching, even when reaching fails, is an essential expression of what we are. The same impulse that drove us to attach that golden record to Voyager is the impulse that drives us to ask whether we can reach Barnard's star. It is the impulse to connect, to extend, to touch something beyond ourselves. The answer in the case of Barnard's star is no. But the asking was not wasted. The asking has taught us about ourselves, about the cosmos, about the limits that define our existence, and the possibilities that persist within those limits. We live in a solar system, one star, a handful of planets, a belt of asteroids, a cloud of comets. This is our home, our entire home, for as long as our species endures. The borders are clear, the boundaries are real, the walls are made of light years, and the lock is the speed of light. But within those walls, there is room for wonder, room for discovery, room for beauty and for meaning. The prison is not small, it is merely finite, and a finite home, understood deeply and inhabited fully, is not a lesser life than an infinite frontier explored shallowly. The stars will continue to shine. Barnard's star will continue its slow journey across the sky, approaching us for another 10,000 years, then receding again, carried by its own momentum through the spiral arms of the galaxy. It has been travelling for billions of years. It will travel for billions more. It does not know we are here. It does not know we have named it, studied it, dreamed about it, calculated the energy required to reach it, and concluded that the journey is beyond us. It is simply a dim old star, burning hydrogen quietly in the dark, alone. We will watch it approach. We will watch it pass. We will measure its progress with instruments of ever-increasing precision. We will search for planets in its orbit, analyze their atmospheres, speculate about their surfaces. We will do all of this from our small world, 4 then 3 then 6 light-years away, never closing the gap, never bridging the void, never converting our observations into arrivals. And yet the observations themselves are a form of connection. Each measurement is a thread between our world and that distant point of light. Each data point is a handshake across the void, incomplete but real, one-sided but meaningful. Barnard's star does not care about our handshakes. The universe does not care about our questions, but we care. And the caring, sustained across centuries and millennia, refined by mathematics and disciplined by observation, expressed in equations and instruments, and the quiet patience of astronomers staring at screens in dark control rooms, is itself a kind of answer. Not an answer to the question of whether we can reach the stars, but an answer to the question of who we are. We are the ones who ask. We are the ones who reach. We are the ones who care enough to calculate the distance, measure the barrier, understand the physics, and still look up with something that is not despair. And in that knowing, there is something that transcends the limitation. Something that, if it is not quite the same as reaching, is perhaps more durable and more beautiful than reaching ever could be. Barnard's star is 6 light-years away. It is a dim, old, solitary red dwarf, smaller than our sun, cooler than our sun, and so faint that you cannot see it with the naked eye. It was discovered in 1916 by an astronomer who noticed it creeping across photographic plates faster than any other star. It has been studied for more than a century. It has been the target of the most ambitious interstellar mission concepts ever designed, and it remains, today, as unreachable as it was when Edward Emerson Barnard first noticed its motion. The reasons are not mysterious. They are not hidden in exotic physics or unresolved equations. They are plain, direct, and inescapable. The distance is too great. The energy required is too vast. The time needed is too long. The engineering challenges are too severe. The biological limitations are too fundamental. The rocket equation is too merciless. The speed of light is too slow relative to the gulf it must cross. Every calculation, every study, every design exercise arrives at the same conclusion, from a different direction, but converging on the same point. 6 light-years, for a species limited by the physics that governs all matter in the universe, is a distance that cannot be crossed in any way that matters. This is not a failure of imagination. It is not a failure of will. It is not a failure of any kind. It is simply the truth about the universe we inhabit. The cosmos is structured in a way that makes interstellar travel extraordinarily difficult, perhaps prohibitively so, for any civilization built from atoms and limited by the speed of light. The distances between stars are not obstacles to be overcome. They are features of the architecture, as intrinsic to the universe as the forces that hold atoms together. The real reason we will never reach Barnard's star is not any single constraint. It is the convergence of all constraints simultaneously: energy, time, mass, radiation, deceleration, reliability, biology, sociology, navigation, communication. Each one is daunting. Together they form a barrier that no technology we possess or can reasonably envision can breach. The universe does not forbid interstellar travel with a clean, simple prohibition. It does something more effective. It makes it so expensive, in every resource that matters, that the effective result is the same as a prohibition. The stars are priced out of our reach, and yet we look. We study, we calculate, we dream. We build telescopes that can see Barnard's star in detail we could not have imagined a century ago. We plan missions we know we cannot build. We design ships we know we cannot fly. We measure the distance and recalculate the energy and refine the numbers and arrive every time at the same answer. Too far, too much, too long, too hard. And still we look, still we calculate, still we dream. There is something in that refusal to stop looking, even in the face of impossibility, that deserves recognition. It is not foolishness. It is not denial. It is the deepest expression of what it means to be a curious species in a universe that rewards curiosity with knowledge but not with access. We can know the stars, we just cannot visit them, and the knowing, for what it is magnificent. Barnard's star does not care about us. It has been burning for perhaps 10 billion years, and it will burn for trillions more. It was ancient when the sun was born. It will be burning long after the sun is dead. It has crossed the galaxy multiple times, passed near countless other stars, travelled through clouds of gas and regions of darkness that no human instrument has ever mapped. It carries no memory of these encounters. It forms no attachments. It asks no questions. It is a ball of fusing hydrogen, massive enough to sustain nuclear reactions, but too small to shine brightly, drifting through the Milky Way on a trajectory that will bring it close to us for a cosmic moment before carrying it away again. We are the ones who noticed. We are the ones who named it. We are the ones who measured its distance, calculated its speed, analyzed its light, searched for its planets, and dreamed about visiting it. And we are the ones who discovered, through decades of careful work, that the visit will never happen. The star does not know it has been studied. The universe does not know it has been understood, but we know, and the knowledge, earned through effort and sustained by wonder, is its own reward. 6 light-years, 57 trillion kilometers, 9,200 years at the speed of the Parker Solar Probe, 106,000 years at the speed of Voyager, forever in any practical human sense. The number can be stated simply, its implications cannot. It means that every human being who has ever lived, and every human being who will ever live, will see Barnard's star only as a point of light, a dim reddish speck, visible only through a telescope, creeping slowly across the constellation Ophiuchus, coming closer year by year, century by century, and never close enough to touch. The stars are not for us. That sentence, stated plainly, is the hardest truth in all of astronomy, harder than the heat death of the universe, harder than the loneliness of the cosmic void, harder than the silence that greets every search for extraterrestrial intelligence. Because those truths are abstract, distant, separated from us by billions of years or billions of light years. This truth is immediate. It is personal. It is about us, right now, and the 6 light years that separate our world from the nearest worthwhile destination. We are not going to Barnard Star. We are not going to Proxima Centauri. We are not going to Alpha Centauri. We are not going to any star. Not with rockets, not with lasers, not with warp drives or wormholes or generation ships or uploaded minds. Not in our lifetime, not in our children's lifetime, not in the lifetime of our civilization. The physics is clear, the numbers are final, the stars are beautiful, and they are beyond reach. But we are here, on this world, under this sky, in this moment, which will not come again. The light from Barnard's star that reaches our eyes tonight left that star 6 years ago, travelling at the fastest speed the universe allows. It has been swimming through the void, crossing trillions of kilometres of emptiness, dodging nothing, touching nothing, connecting our world to that distant point of light by the thinnest possible thread. And when it arrives, when it strikes the lens of a telescope or the retina of an eye, it completes a connection that no spacecraft will ever make. Light is the only bridge, photons are the only messengers, and the messages they carry, decoded by our instruments and interpreted by our minds, are the only contact we will ever have with the wider cosmos. That is enough. It has to be enough, because it is all there is. We live in a universe that shows us everything and lets us touch almost nothing. We are surrounded by beauty that we cannot reach, by mysteries that we cannot visit, by worlds that we cannot walk on, by stars that we cannot orbit. And yet we look, we always look, we measure, we understand. We feel the pull of the unreachable and we do not turn away. We never turn away. It is not in our nature. It never has been. And perhaps that is the most remarkable thing about us. More remarkable than our tools, more remarkable than our equations, more remarkable even than our ability to understand the physics that confines us. We look at what we cannot have, and instead of closing our eyes, we open them wider. The stars are 6 light years away, and they are right here, in the light that fills our instruments, in the equations that fill our notebooks, in the wonder that fills our minds. They are out of reach, and they are in our hands. They are impossible to visit, and they are impossible to ignore. They are the great unreachable, the luminous boundary of our world, the edge of everything we can know and the beginning of everything we cannot. Barnard's star burns quietly in the dark. It does not know our name. It does not hear our questions. But its light reaches us, steady and ancient and red, crossing the void at the speed of the universe allows, carrying nothing but information and asking nothing in return. And we receive that light. We study it. We honour it with our attention. And in the silent exchange between that distant fire and these restless minds, something happens that is, perhaps, as close to a miracle as physics permits. Stardust recognizes starlight. Matter understands matter. And for a brief moment, across 6 impossible light years, the universe is not entirely alone.